I've got a bit of trivia for you guys. A 50-year-old woman, no symptoms, participates in routine screening for breast cancer. She tests positive, is alarmed, and wants to know from you whether she has breast cancer for certain or what her chances are. Apart from the screening results, you know nothing else about this woman. The prevalence of cancer among women her age is 1%, and the test is 90% accurate. 90% of the time, it gives the correct diagnosis as to whether or not someone has the disease. So the question is, in light of her positive test result, what are the woman's chances of having cancer? Is it 80%, 90%, 22%, 8%, or 1%? You can think about that for a second, come up with your answer. I'll wait. Now, you might have said B, and if so, I'm sorry to say, but that's wrong.
It's false. No way. Not this time. We created it. Not this time. No, not this time.
The answer is actually D, 8%. And after watching this video, you'll know exactly why that is. Welcome everyone to the Majesty of Reason. I'm Joe Schmid, and today we're talking about Bayes' theorem. This video is actually requested by a patron, Jeremy, so thank you, Jeremy, so much for your support. If you guys see value in the work that I do, consider becoming a patron. There are so many perks included, such as exclusive videos, notes, papers, books, and depending on your level, personal meetings with me and video requests. All patrons, by the way, have access to the 37-page script that I made for this video. But anyway, back to Bayes' theorem. So, named after Reverend Thomas Bayes, an 18th century English statistician, philosopher, and Presbyterian minister, Bayes' theorem is a powerful tool for updating our beliefs in light of new evidence. Its applications range from artificial intelligence and machine learning to medicine and science to philosophy and well beyond. My goal in this video is to give you a foundational understanding of what the theorem says, why it's true, how to use it, and how not to use it. Also, don't worry if this all sounds intimidating or beyond your grasp. I'm going to try to make it as accessible and understandable as possible. So even if you're not a math person, or even if you're somewhat new to philosophy, or you haven't studied probability theory or statistics, this video shouldn't be too daunting. It may stretch you at times, but I'm here to help as much as I can. All right, so all of y'all know that I love my outlines. I'll begin by briefly introducing Bayes' theorem itself, after which I'll give some background on belief and credence and probability and things like that. Then we'll look at the theorem itself, and in particular, we're going to be looking at two different forms of the theorem, as well as how it interacts with the Bayesian notion of evidence or evidential confirmation. We'll also be considering some proofs of Bayes' theorem, why we know that this is true, how we know that it's true, and something very exciting, or at least I find very exciting, I find it titillating, is visualizing Bayes' theorem. So we're going to walk through some videos about how to visualize Bayes' theorem and how to think about probability visually. It's super duper helpful, trust me. We'll then look at some pretty common mistakes to avoid when using Bayes' theorem and assessing Bayesian arguments. And finally, I'll end with pointing you guys to some helpful resources. And note that all throughout the video, we'll be applying the theorem to tangible problems. All right, but the big question in this first section is, what even is Bayes' theorem? Well, Bayes' theorem is many things. The simplest answer is that Bayes' theorem is a mathematical equation, expressible in several different forms, that allows us to calculate conditional probabilities, where a conditional probability is the probability that one claim is true given that another claim is true. It also follows strictly from the axioms of probability theory. I'm going to explain how that is later, but that's all that you need to know right now. That's why it's called a theorem. A theorem is basically what you can prove to be the case within a given axiomatic system. But Bayes' theorem is far more than a mere equation that follows from the axioms of probability theory. It's also a powerful tool for updating our beliefs in light of new evidence. It's a powerful tool for assessing the probability of various hypotheses in light of data, and that relates to confirming and disconfirming theories, getting evidence for and against theories. It's also a formal constraint on rational credences. That is, it's a constraint that your confidence in various statements needs to meet in order to be rational. Don't worry, I'm going to be talking about what credences are soon. Right now, I'm just giving you a bird's eye view of what Bayes' theorem is. So yeah, if you're interested in being rational, which I presume you are, you should be interested in Bayes' theorem, since the theorem expresses how your credences, or your confidence levels, or your degrees of confidence should rationally change in order to account for new evidence. Now, again, this is a very coarse-grained articulation of Bayes' theorem, and I'm not even putting the theorem on the screen yet because we don't have the requisite background to be able to understand it yet. For this section, again, I'm just trying to give you a bird's eye view. As we progress through the video, we'll gain a deeper understanding of the theorem, its significance, and its applications. Before getting to the theorem itself, however, we need to cover some essential background on belief, credence, probability, and Bayesian epistemology. Don't worry, I'm going to try my best to make this as accessible as possible. Let's turn to belief and credence. So most of epistemology concerns propositional attitudes. A propositional attitude is an attitude that an agent adopts toward a proposition. While a lot of ink has been spilled over the nature of propositions, here we'll just treat them as the meanings of declarative sentences. They're basically what sentences express. They're also capable of having truth values. That is, they're capable of being true or false. So, for example, the sentence, nuclear fusion is a viable energy source, that sentence on the screen there, expresses the proposition that nuclear fusion is a viable energy source. If I believe that fusion is viable, this belief is a propositional attitude. It's an attitude that I take toward the proposition that fusion is viable. Epistemology focuses in particular on propositional attitudes that attempt to represent what the world is like. Belief is in some sense a purely representational attitude. When we attribute a belief to someone, we're simply trying to describe how they take the world to be, or how they represent the world as being. We're saying that they're taking a stance on the relevant proposition, that they're affirming its truth, that they're taking it to be true, or representing the world as being the way the proposition says it is. That's what we're saying when we say that someone believes a proposition. And belief, of course, is not the only purely representational attitude that an agent can have toward a proposition. An agent might also be certain that a proposition is true, or disbelieve a particular proposition, which is, in other words, believing that the proposition is false. Philosophers often discuss the class of doxastic attitudes into which belief, disbelief, and certainty all fall. Doxastic attitude, by the way, is an umbrella term for propositional attitudes that are belief-like. Doxa is Greek for belief, in fact. And they're belief-like in the sense of being purely representational attitudes. And so doxastic attitudes, that category includes things like belief, of course, but also disbelief, certainty, doubt, suspension of belief or suspension of judgment, credence or confidence level, and others. Now, Bayesian epistemology in particular focuses primarily on a type of doxastic attitude known variously as degrees of belief, or degrees of confidence, or levels of confidence, or credences, and that's a term that we're going to be going with going forward. Your credence in a proposition is basically how confident you are in that proposition. It's your degree of confidence in it, and it's represented using a quantitative degreed scale from 0% to 100%, or from 0 to 1. 0 representing 0% confidence in something, and then 1 representing 100% confidence, and then, of course, everything in between. 0.75 would be 75% confidence in a proposition. So, for instance, you might be 100% confident, that is, absolutely certain that 1 plus 1 equals 2. You might be 0% confident that triangles have 4 sides. That is, you're absolutely certain that that's false. You might be 50% confident that the number of stars in the universe is even. You might be 80% confident that it will rain tomorrow, and so on down the list of your credences. All of these numerical descriptions represent your credences in the various propositions just mentioned. Philosophers generally like to use the 0 to 1 scale, so your credence in those propositions would respectively be 1, 0, 0.5, and 0.8. And going forward, I'm going to be mostly using the 0 to 1 scale, though occasionally context will make clear when I'm using the 0% to 100% scale. So at this juncture, I think it's useful to ask, firstly, what's the difference between beliefs and credences? And also, why should we countenance credence in addition to beliefs? That is, why should we even believe that there are such things as credences? Why not instead just simply represent our doxastic lives as merely containing beliefs? Why do we have to postulate credences in addition? Or why do we have to describe ourselves as having credences in addition? Well, on that first question, beliefs are binary, right? Given any particular proposition and any agent, the agent either believes it or doesn't. End of story. But credences aren't binary like that, right? They're quantitative and graded in a way that beliefs aren't. Your belief is simply how you take the world to be, whereas a credence represents your degree of confidence in taking the world to be that way. It's basically about the certainty or confidence with which you hold your beliefs. But on that second question, as to why we should even countenance both beliefs and credences, the first thing to note is that, at least for many propositions, it just seems introspectively obvious that we have credences. We simply find ourselves with different degrees of confidence in different propositions. And these aren't binary, but are rather graded, right? For some things, we're very confident, others less so, and still others we're not at all confident in them. So that's the first point. But secondly, if we only described agents as doxastic attitudes with beliefs, we'd be unable to account for many facts about agents' doxastic lives. To account for those facts, we need to be able to attribute quantitative attitudes to agents. That is, we need to countenance credences. So this is the point here about explanatory power. We basically need to explain various facts about agents' doxastic lives. And to do that, we need to have credences in our repertoire. So suppose my physicist friend believes that nuclear fusion is a viable energy source. She also believes that her car will stop when she presses the brake pedal. She's willing to bet her life on the latter belief, and in fact she does so multiple times daily during her commute to and from work. But she's not willing to bet her life on the former belief, right? She's not willing to bet her life on nuclear fusion being a viable energy source. This difference in the decisions she's willing to make seems like it should be traceable to a difference between her doxastic attitudes toward the proposition that fusion is viable, on the one hand, and the proposition that pressing her brake pedal will stop her car, on the other. Yet, if we don't countenance credences, we'll be unable to make out any difference between my friend's doxastic attitudes toward those propositions, right? Once we note that my friend believes both propositions, that's all we'd be able to say. Unless, of course, we avail ourselves of credences, right? If we don't avail ourselves of credences, then all we can say is that, yeah, she believes one, she believes the other, but we can't explain her differences in risk-involving decisions. In one case, she bets her life on the proposition, and in another case, she doesn't. Now suppose my physicist friend reads about some new research into nuclear energy. The research reveals new difficulties with designing more efficient nuclear power plants, which will make fusion power more challenging going forward. After learning of this research, she still believes fusion is a viable energy source. She has mountains of evidence, we can suppose, for thinking that that is the case. And this recent research is only a small piece of evidence being added to that monstrous pile of evidence. So she still believes fusion is a viable energy source. Nevertheless, it seems that this new evidence should cause some change in her attitude toward the proposition that fusion is viable. Yet if we don't countenance credences, we lack the tools to ascribe any such change, right? My friend believed the proposition beforehand, and she still believes it now. She still has belief both before and after learning this evidence against her belief. So if we only availed ourselves of beliefs, we'd be unable to explain the change in her attitude toward the proposition that fusion is viable. And what that means is that we need beliefs and credences in order to describe her doxastic life and, more generally, agents' doxastic lives at large. So we've been talking about credences and ascribing credences to agents, but of course, all of this is at best a kind of idealization. In truth, there isn't usually a precise answer to the question of exactly how much I'm confident in the truth of P for every single proposition P. There are plenty of propositions that I've never even thought of, and even among those that I have thought of, many of those are such that I've got a pretty fuzzy attitude towards them. Nor is it very realistic to suppose that I can attach numbers to all the things that I care about. Still, we can go along with the idealization in order to simplify our discussion going forward. But credences, of course, aren't only a useful simplification, since for at least a good deal of propositions, credence ascriptions at least roughly capture our degreed levels of confidence toward those propositions. And as we saw when covering some of the reasons to believe in credences in the first place, talk of credences seems both justified and quite important for capturing elements of our doxastic lives. So yes, there's some idealization and simplification involved here, but there's also utility and approximate accuracy. We are really picking out something in our doxastic lives. What we're picking out is going to be a little bit more messy and a little bit more fuzzy than our very precise mathematical models, but they're still approximately accurately describing the phenomenon, at least in many cases. Of course, credence ascriptions do have some disadvantages. For instance, numerical representations may provide more specific information than is actually present in the situation being represented. Similarly, I might be more confident that the Democrats will lose the next election than I am that they will win, without there being a fact of the matter about exactly how much more confident I am. Representing my attitudes by assigning precise credence values here to the proposition that the Democrats will lose and the proposition that they'll win attributes to me a confidence gap of a particular size. And that may be over-attributing things to my doxastic life. And also, assigning numerical credences over a set of propositions creates a complete ranking among them, which makes it impossible to retain any incommensurabilities among the propositions involved. Incommensurabilities basically means like there's no way to compare the relevant beliefs in terms of some metric. And yet you might worry that confidence incommensurability, that is, for at least some propositions, your confidence in one may simply be not even commensurable with your confidence in another. There may be no common metric by which you could compare them. You might think that that's a common and rational feature in agents' doxastic lives. So again, there's idealization, there's simplification involved here, but at least for many propositions, it's plausible that agents' doxastic attitudes can be usefully and approximately accurately represented as credences, or numerical degrees of belief. Now, credences are closely related to the notion of probability in Bayesian reasoning. Given a proposition P, we can speak of the probability of P. For instance, the probability that the next card from this pack will be an ace, the probability that this radium atom will decay before the year 2100, the probability that it will rain tomorrow, and so on. We can write P of P, or PR of P, to represent the probability of P. Sometimes you'll also see CR of P, and that's just representing an agent's credence in P, so keep these notational variants in mind. But the major question of this section is, what is probability? What are we even talking about when we're talking about the probability of one statement or the probability of H given E or those sorts of things? Well, usually probability is introduced first through a distinction, and that distinction is between two broad kinds of probability: objective probability and subjective probability. Objective probabilities are mind-independent features of reality. They're features out there, as it were. For instance, there might be an objective probability of 50% that an indeterministic atom will decay within the next hour. This probability doesn't depend on us in any way. For instance, it's not a measure of our credence or our degrees of belief. Instead, it's a matter of some objective feature of the atom itself, perhaps some propensity or tendency inherent to it, or perhaps it's a statistical fact about the frequency of decays among atoms of its kind, or perhaps it's something else entirely. What matters here is that this probability is objective, or mind-independent. It's a feature of the world out there. It doesn't depend on our attitudes or our subjective mental states, etc. By contrast, subjective probabilities are, you guessed it, mind-dependent. And one dominant way of understanding subjective probabilities simply identifies them with credences, or degrees of belief. So an agent's subjective probability in a proposition just is their credence in that proposition. Some philosophers, though, think this distinction between objective and subjective probability confuses more than it illuminates. Perhaps there are really a panoply of different notions of probability, some of which are entirely mind-independent, some of which are entirely mind-dependent, and others of which have some aspects which are mind-independent, and other aspects which are mind-dependent. And speaking of a panoply of different notions of probability, that brings us to different interpretations of probability, different interpretations of probability talk, and different interpretations of probability itself. Like, what is a probability? What is this feature that we're picking out? Now, before I go through these and explain them, note that some people argue that all probability claims are captured by just one of these understandings of probability, or one of these interpretations of probability. But I don't think that's plausible. I think that in different contexts, we use different notions of probability. Sometimes we're talking about frequencies, sometimes we're talking about propensities or tendencies, sometimes we're talking about what credences someone actually has, sometimes we're talking about what credences are rational or what credences someone should have, and so on down the list. I doubt that any of these is, quote-unquote, the notion of probability. Instead, they're all different ways of using probability talk in different contexts. As a result, I'll simply treat each of these interpretations of probability as a distinct way of understanding probability talk, and which understanding is at play when certain parties are engaged to a debate or engaged to a discussion, or when you're reading a paper or a book or listening to a video, which understanding is at play will largely depend on context. But anyway, here are some of the major interpretations of probability on offer. Oh, and I should note that I left off this list the so-called classical interpretation of probability because it totally fell out of favor like a long while back. But according to that view, probability is basically counting the number of favorable outcomes out of the total number of possible outcomes. So if you're asking about the probability of rolling 6 on a die, to say that the probability is 1/6 is to say that there's one way of rolling a 6 out of the total number of possible rolls. So it's one way out of 6 ways, so 1/6. So anyway, that's the quote-unquote classical interpretation of probability. I left that one off the list. Okay, anyway, we're moving on to the list now. So one understanding treats probabilities as objective tendencies or propensities for certain outcomes. Propensities are, roughly, degrees of causal influence. Different sets of causal factors have stronger or weaker tendencies to produce certain outcomes, and probabilities measure the strength of those tendencies or propensities. This is arguably the notion of probability at play in quantum indeterminism. If that's so, well then when we say that a radioactive atom has a 50% probability of decaying in a given time period, we're attributing to the atom, perhaps together with its environmental conditions, a certain quantitative propensity or tendency or inclination or disposition to decay. these tendencies would still have existed even if agents with credences had never existed. So this is an objective understanding of probability. Another understanding treats probabilities as the frequencies of certain outcomes or events under such and such conditions, where those frequencies can be understood as either actual frequencies or hypothetical frequencies. For example, the frequency with which the outcomes would occur if those conditions were repeated many times, perhaps even infinitely many times. Again, this is quite clearly an objective understanding of probability. There's a fact of the matter, independently of us, with what frequency a certain outcome or event would occur or obtain under certain conditions, if those conditions were repeated. A further understanding treats probabilities as an agent's actual credences or degrees of belief. On this understanding, probability is always relative to an agent. You can only ever talk about an agent's probability for a given proposition. And it's also talking about their actual credences. So probabilities on this view are thoroughly mind-dependent. And this is therefore a subjective understanding of probability. In fact, as we've seen, many people simply identify actual credences with subjective probabilities. Like, to say that someone has a credence of 0.5 in something is to say that their subjective probability is 0.5. But anyway, what matters for present purposes is that this is one way of talking about probability. This is one interpretation of probability. A related understanding treats probability as rational credences, or rational degrees of belief. That is, the credence an agent should have in a proposition in light of their evidence, or perhaps in light of a restricted set of facts in the case of unconditional probabilities. Don't worry, I'll talk about unconditional probabilities later. Now, there's the question, is this an objective or subjective understanding of probability? Well, there are elements of both here, I think. Once you fix the evidence you're taking as input, there's arguably a perfectly objective fact of the matter about what the rationally appropriate credence in a proposition is in light of that body of evidence, which bears on the truth of that proposition. So there's an element of mind independence here. But there's also a clear element of mind dependence here, since that input body of evidence is always an agent's body of evidence, right? And that's going to vary by agent, and it's going to depend on various facts about the agent. So again, probabilities here are rational credences in light of evidence. So you have a kind of output, which is the rational credence, and then you have the input, which is the evidence, and the probability is like the function, which takes that input and spits out the output, takes the input of the evidence, spits out the output of the rational credences. So with that in mind, another element of subjectivity within this account is that the output of the probability function, that is the rational credence one should take in light of the input evidence, is still a credence, right? Albeit a credence that an agent should have. Still, because it's a credence, there's a sense in which it's a property of agents. And so this is another element of mind dependence in this account. But anyway, that's another interpretation of probability. Viewing probabilities as rational credences, what credences agents should have in light of their evidence. A still further understanding treats probabilities as mind-independent, degreed relations of support between propositions. And these degreed relations of support between propositions, in turn, determine which degrees of belief are rational. Importantly, though, these mind-independent degreed relations of support between propositions are not themselves degrees of belief. They determine which degrees of belief are rational, they determine which credences are rational, but they are not themselves credences. This view is defended by Nevin Klimenhaga and others. Also note that under this account, the unconditional probability of a proposition is the degree to which the proposition is supported by a priori truths or tautologies. And I'll define tautologies soon, so don't worry about that. This view is easy to categorize. It's a thoroughly objective understanding of probability. And then a final interpretation of probability that we're going to talk about here is one that's pretty closely related to the rational credence account, but it treats probability as a measure of the degree of justification that a proposition has in light of one's current evidence. It differs from the rational credence one because it's not saying that probabilities are rational degrees of belief, but instead it's saying that probabilities are degrees of justification. And one might think that those can come apart in principle. So a proposition has probability of 1 in this understanding of probability, just in case we have conclusive justification, that is the strongest justification possible for believing it. And that applies to, at most, very few propositions, like perhaps the proposition that something exists or that 2 is less than 3. And a proposition has probability 0 for us on this understanding of probability, just in case we have conclusive justification for denying it. And so the proposition that I do not exist has, for me, right now, a probability of 0, as does the proposition that 1 equals 4. Generally speaking, on this account, the only propositions with probability 0 are going to be those that are contradictory or otherwise absurd. Now, like the rational credence account, this account has both objective and subjective elements. Probability, under this view, is in principle relative to an individual, right? A proposition may have different probabilities for different individuals if those individuals have different evidence. So this is an element of mind dependence within this account. But there's also an element of mind independence, since it's an objective matter to what extent your evidence justifies a given proposition. Now, note that there are other interpretations of probability besides these. I just want to give you a flavor of some of the main ones on the table that philosophers discuss. Now, you may have heard of epistemic probability. This is a term that's used differently by different philosophers. Sometimes it's used interchangeably with subjective probability, that is, credence, but I would strongly caution against that usage. Instead, I think epistemic probabilities are best understood minimally as the probabilities we reason about in epistemic contexts, where an epistemic context is a context in which we reason about things like how probable a scientific theory is, or how strongly a theory, whether scientific or not, predicts some evidence, or to what degree some evidence confirms a theory or hypothesis, etc. It's then an open question which of the above understandings of probability, if any, epistemic probability should be identified with. It's also then an open question whether epistemic probability admits of different precisifications in different contexts. And that's a good result, since there's disagreement among philosophers on that very question. Now, to give you a glimpse into different usages or different understandings of epistemic probability, Tyler Hildebrand and Thomas Metcalfe, in their news article on the nomological argument for God's existence, they seem to use epistemic probability to refer to a probability pertaining to your credences, and then they divide up epistemic probability into subjective and objective epistemic probabilities. So subjective epistemic probabilities describe your personal credences in the relevant propositions. That is, they describe what your credences are. Whereas objective epistemic probabilities describe how strongly you ought to believe the propositions given your total evidence. That is, what your credences ought to be. And know that that's not a moral sense of ought. Like, no one is saying here that you're a bad person, you're an immoral person, etc. This is an epistemic sense of ought. It's basically what's rational or justified or something like that, what's rationally appropriate. And those of you who are paying attention will notice that this objective epistemic probability, the way that Hildebrand and Metcalfe articulated, is just the rational credence account that I talked about under the interpretations of probability. But other people view epistemic probability quite differently. For instance, Mike Humer understands epistemic probability as degrees of justification, and Nevin Klimenhage argues that epistemic probability is best understood as degrees of support. So the degree of support view, Nevin Klimenhage argues that that's the best understanding of epistemic probability. Mike Humer argues that the degree of justification account is the best, and still others go for different interpretations. So as you can see, there are a number of different accounts of probability on offer, and there are also different ways of spelling out what epistemic probability is. In light of that, I'd suggest that if you're going to use a term for a view, if you're going to use the term epistemic probability, or even probability for that matter, I just recommend explicitly defining how you understand the view as you introduce the term for it. And that way we don't have to engage in linguistic squabbles. So for instance, you could just say, well, okay, listen, by epistemic probability, I mean this. Or you might say, by epistemic probability, we should mean this because it's the best way of interpreting what we do in epistemic contexts, etc. Anyway, you get my point. So all of this is meant to serve as tools for your conceptual toolkit. Going forward, we'll mainly just talk in terms of probability, since that's all we really need to talk about in order to understand the basics of Bayes' theorem. Which precise notion of probability is at play will largely be determined by context or stipulation. But just a note that going forward, I'm mainly going to be talking in terms of just probability. It's important, though, to have these tools in your conceptual toolkit. It helps you weed out confusion about probability. It helps you identify distinct notions of probability and potentially disambiguate them when they come up in your thinking and the thinking of others. And ultimately, it's a path toward a greater understanding of reality and a greater understanding of probability and Bayes' theorem itself. We can turn to Bayesian epistemology. So Bayesian epistemologists study norms governing credences, including how credences ought to change in response to a varying body of evidence. And at least generally speaking, Bayesian epistemology addresses epistemological problems with the help of the mathematical theory of probability. It turns out that the probability calculus, that is the mathematical theory of probability, is especially suited to represent credences, or degrees of belief, and to deal with questions of belief change, confirmation, evidence, justification, coherence, and more besides. Compared to the informal discussions in traditional epistemology, Bayesian epistemology allows for a more precise and fine-grained analysis of these epistemological problems and issues. Bayesian epistemology therefore complements traditional epistemology. It doesn't replace it or even aim at replacing it. Now, although I've been talking here about Bayesian epistemology and Bayesian epistemologists, unfortunately there's really no single Bayesian epistemology. Instead, there are many Bayesian epistemologies. Nevertheless, any Bayesian epistemology characteristically endorses the following two principles that you can see on screen here. Firstly, agents have certain doxastic attitudes, namely credences, that can be usefully represented by assigning real numbers to propositions. Secondly, rational requirements on those credences can be represented by mathematical constraints on the real number assignments given by the probability calculus. Now again, the probability calculus, that's just the mathematical theory of probability. It includes the axioms of probability, the formal language within the theory, what logically follows from those axioms, etc. So these are two characteristic principles that Bayesian epistemologies endorse. Firstly, agents have credences, and we can represent those by assigning real numbers to propositions. And secondly, there are certain rational requirements on those credences, and we can represent those rational requirements with the help of the mathematical constraints provided to us by probability theory. We've already touched on the first principle, and so we can now consider the second principle. On the second principle, credences are subject to various rational constraints or requirements, and these constraints are given to us by various elements of probability theory. These rational constraints or requirements are also known as normative rules, in that they're standards for how we should reason. So we're not necessarily talking about how we in fact reason, but instead how we should reason, how we ought to reason. These are normative rules, normative standards that we should live up to. Now, there are 5 core normative rules of Bayesian epistemology: Kolmogorov's 3 probability axioms, the ratio formula, and the conditionalization principle, also sometimes called the principle of conditionalization. This isn't to say that these are the only normative rules that Bayesians accept, but you can't understand any additional rules without understanding these 5 first. They also serve as the basis for understanding Bayes' theorem, which of course is what we're building up to, right? This is a video about Bayes' theorem, but we've got to build up to that first. We need to have certain foundational knowledge so we can have a deeper understanding of Bayes' theorem and its use and its significance and its applications. So what we're going to do going forward is basically just going through these core normative rules and explaining them. Before doing that, though, we should at least get 3 important notes on the table. First, it should be noted that these normative constraints are sometimes articulated in terms of rational credence, which in turn means that they'll be articulated using CRP, CR not Q, CRP or Q, etc. Other times, however, they're articulated in terms of probability, which means that they'll instead be articulated using P of P of not Q, etc. Going forward, I'll articulate the normative rules in terms of probability. I think this is more illuminating because it emphasizes that the rules are not merely descriptions of actual credences. Our actual credences are often inconsistent. They often flout or violate the normative rules of Bayesian epistemology. And CRP, right, this little formalism here, CRP, that can easily mislead you into thinking that we're talking about someone's actual credence in P, rather than what credence it's rational to have in P. And in fact, in some contexts, CRP is used to refer to someone's actual credence. So expressing the normative rules in terms of probabilities allows us to more clearly see that these are rational constraints on agents' credences. They are not mere descriptions of actual credences, but instead constrain what credences are rational. They set bounds around what credences one rationally ought to have. If you're in the rationality business, in other words, you need to respect these rules. So going forward here, when I speak of probabilities in articulating these 5 core normative rules, you can helpfully think of them as rational credences. Not actual credences, but rational credences. But I mean, again, for clarity, I'm going to be using probability talk. I'm just going to be talking about the probability of P, probability of not Q, and so on. All right, so that's the first note. The second note is that we need some very basic background in propositional logic before introducing the normative rules. In propositional logic, we have a propositional language. And this propositional language contains atomic propositions that are usually represented using the letters P, Q, R, and so on. Atomic propositions, by the way, are just propositions that don't embed any larger constructions within them. They're basically like simple. They're the building blocks of larger constructions. So an atomic proposition might be grass is green, and a non-atomic proposition might be the conjunction of grass is green and the sky is blue. It's a construction out of the atomic propositions grass is green and the sky is blue. Atomic propositions are the atoms from which those constructions are built up. Okay, so our propositional language includes atomic propositions, and it also includes various connectives. These are called connectives because very often they connect different atomic propositions together to form larger constructions. So once we have our atomic propositions, the rest of the propositions in our language are constructed from the atomic propositions using these 5 propositional connectives. This little sign for negation, this ampersand for conjunction, or for disjunction, a single arrow for material conditional, and a double arrow for material biconditional. Don't worry, this background in propositional logic is not going to get too convoluted, too complicated. Again, I'm going to try to make this as accessible as I can. But anyway, here's how these connectives work. A negation, not P, so that's how we're going to read that. A negation, not P, is true just in case P is false. So if not P is true, then P is false. And moreover, if P is false, then not P is true. Not P, in other words, is just equivalent to the falsity of P. A conjunction, P and Q, is true just in case both of its conjuncts, namely P and Q, are true. So if the conjunction is true, then each of P and Q is true. And moreover, if each of P and Q is true, then the conjunction P and Q is true. It's false otherwise. So if at least one of these is false, then the whole conjunction is false. A disjunction, P or Q, is true just in case either P is true or Q is true, or both P and Q are true. In other words, the disjunction is true just in case at least one of its disjuncts is true. And the disjuncts, of course, are just the individual atomic propositions within the disjunction. And so the disjunction is therefore false exactly when both of its disjuncts are false. So in order for P or Q to be false, both P and Q need to be false. Otherwise, this disjunction as a whole is true. A material conditional, also called material implication, and usually we're going to read this as if P then Q, or P implies Q. A material conditional like this is false just in case P is true while Q is false, and the conditional is true otherwise. So a material conditional as a whole is going to be false exactly when its antecedent, the if part, the part before the arrow, exactly when its antecedent is true, and yet its consequent is false. Its consequent is the then part. It's the atomic proposition after the arrow. But the material conditional is true in every other case. So if at least one of these conditions aren't met, if either P is false or Q is true, well then the material conditional as a whole is going to be true. The reason I put this in terms of falsity is because I think that's the easiest way to get your mind around it. Like, imagine that I say, if you get a 90 or above on this test, you get an A. Well, like, under what condition is what I just said false? Well, it's exactly under the condition in which you get something above a 90% on the test, and yet you don't get an A, right? So it's the condition where the antecedent is true, you did get above a 90% on the test, and yet the consequent is false, where I don't give you an A, right? That's exactly when what I said is false. And think of the material conditional as true in all other cases. Okay, so that's a material conditional. And then finally, a material biconditional, P if and only if Q, or P just in case Q, or P exactly when Q. That material biconditional is going to be true just in case P and Q have the same truth value. That is, just in case either both are true or both are false. So if these two differ in their truth value, if one's true while the other is false, well then the material biconditional as a whole is going to be false. But the material biconditional is going to be true so long as these two agree in their truth value, as long as they're both true or they're both false. Okay, so that's some background on atomic propositions and the various truth functional connectives. So we also need to know going forward what a tautology is and what a contradiction is. A tautology, T, is a construction that's guaranteed to be true by its logical form. Any way of assigning truth values to T's propositional symbols results in T itself being true. So whenever you have a construction and you look at its propositional symbols, this one only has one propositional symbol, P. Of course, it recurs, but it's still the same propositional symbol. It's P rather than Q or R or S. Any way that you assign truth values to P, so whether you assign true to P or whether you assign false to P, the construction as a whole is guaranteed to be true. That's what a tautology is. And so T is in that sense logically necessary, right? It's necessary that T is true because of its logical structure. And examples here of tautologies are going to be things like, it's not the case that both P and not P. I mean, think about that. It's not the case that P is true and P is false. Yeah, I mean, that's guaranteed to be true by its logical form. Like, whether P is true or false, whether, for instance, I exist or not, it's still going to be true that it's not the case that I both exist and don't exist. So whatever way you assign truth values to the propositional symbols here, the construction as a whole is going to be true. It is logically necessary. There's no way for it to be false. It just logically cannot be false. You could also think of it as saying denying a tautology is going to be a contradiction, but I haven't even defined contradiction yet. So another example of a tautology is P or not P. That's guaranteed to be true by its logical form. It's logically necessary that either I exist or I don't exist. P implies P is also a tautology. If I exist, then I exist. Or if I don't exist, then I don't exist. Both of those constructions are true. Any construction like that is guaranteed to be true by its logical form. A contradiction, by contrast, is a construction that's guaranteed to be false by its logical form. In other words, any way of assigning truth values to its propositional symbols results in it being false. And so contradiction is in that sense logically impossible. Its truth is impossible because of its logical structure. Examples of contradictions include P and not P, right? So it's just a contradiction to say I exist and I don't exist. Another example of a contradiction is P if and only if not P. Because remember, given how the biconditional is defined, the biconditional as a whole is only ever going to be true if these two share their truth value. And yet, P and not P can never share the same truth value, because then P would be both true and false. So yeah, a contradiction is a construction that's guaranteed to be false by its logical form. All right, we just have two more small pieces of background in propositional logic before we get on to the 5 core normative rules of Bayesian epistemology. The first is about mutual exclusivity. So the propositions in a set are mutually exclusive just in case the truth of any one member of that set logically entails the falsity of all the other members of the set. Thus, no logically possible world makes more than one of the propositions in the set true. To put it differently, each proposition in the set is incompatible with all the rest. So for example, the set containing P and not P, like that set is mutually exclusive because the truth of any one member of the set logically entails the falsity of the rest of the members of the set. The truth of any one of the members of the set precludes the truth of all the others. If one of them is true, the rest of them can't be true. And so they mutually exclude one another from truth, as it were. And then the second piece of conceptual machinery that we need to get on the plate is logical entailment. So a proposition P logically entails a proposition Q just in case it's logically impossible for P to be true while Q is false. So the conjunction P and not Q is a contradiction. It is literally contradictory to say that P is true while Q is false, and so P logically entails Q. Another way to put this is that in any logically possible world in which P is true, Q is also true. P, just in virtue of its logical form, implies Q, or P implies Q is a tautology. All of these are basically the same way of conveying logical entailment. Alright, so that's all the background that we need in propositional logic. I hope you stuck through it. If so, congratulations. I hope we didn't lose any arms or legs or souls. So the third and final note going forward is really just anticipating a question you might have. In particular, you might be wondering, like, Joe, why haven't we gotten to Bayes' theorem yet? Give me the Bayes. Now listen, I understand your eagerness for Bayes' theorem. Truly, I understand it. And I applaud you for your eagerness to cover the almighty equation. But I have an answer for you, okay? The reason why we haven't gotten to Bayes' theorem yet is that to truly understand Bayes' theorem, to have a deep grasp of what it is, what it's saying, and why it's true, you need to know a sizable chunk of background information. Bayes' theorem follows from the axioms of probability theory. That's how we know that it's true. And these axioms are the ones that we're about to cover. To understand Bayes' theorem, then, it's important to understand those axioms. And to understand those axioms, you need to know some important facts about propositional logic and about probability, and about how these various axioms are not about actual credences, but instead represent rational constraints on credences, etc. That is why we have taken the facially circuitous route that we have. It is only facially circuitous. It is not in fact circuitous. I think this is a really good way to teach Bayes' theorem. But okay, having covered all that, we can now proceed to the 5 core normative rules of Bayesian epistemology, beginning with the first 3, and these 3 are, of course, Kolmogorov's axioms. The first such axiom is called non-negativity. It says that for any proposition P, the probability of P is greater than or equal to 0. And you can see why it's called non-negativity. It's saying that the probability of any proposition is not negative. The second Kolmogorov axiom is called normality. It says that for any tautology T, the probability of T is 1. And that makes sense. A tautology is guaranteed to be true by its logical structure, and so there's a 100% probability that it's true. The probability that it's true is 1. There's literally no logically possible way for a tautology to be false. The third axiom is finite additivity. It says that for any mutually exclusive propositions, P and Q, the probability of P or Q is equal to the probability of P plus the probability of Q. And remember, P and Q are mutually exclusive just in case they're incompatible with one another. The truth of one logically entails the falsity of the other. Now, Kolmogorov's axioms are often referred to as the probability axioms. The great 20th century Russian mathematician Andrei Kolmogorov was the first to articulate these axioms as the foundation of mathematical probability theory, or the probability calculus. But yeah, that's it for the first 3 normative rules of Bayesian epistemology. Pretty simple. Now, actually, things get a little more complex, since these axioms have lots of very important consequences. One immediate consequence of them is that the probability of not P is equal to 1 minus the probability of P. So, for instance, if the probability that it will rain is 0.3, well, then the probability that it won't rain is 0.7, right? It's just 1 minus 0.3, which is 0.7. I mean, that makes intuitive sense, but to see why this follows from the axioms, note that P and not P are incompatible, and so they're mutually exclusive. And so by finite additivity, right, which says that for any mutually exclusive propositions P and Q, the probability of P or Q is just equal to the sum of the probabilities of P and Q, we can get that the probability of P or not Q is equal to the probability of P plus the probability of not Q, right? But P or not Q, that's just a tautology, right? That is guaranteed to be true by its logical form. That is logically necessarily true. Any way of assigning truth values to its propositional symbols results in the construction as a whole being true. And so, since that's a tautology, we can conclude by normality that its probability is 1, right? So the probability of P or not P is 1. But now look what we have, right? We have the probability of P or not P. We got the probability of P or not P here. So because this is equal to this, and because these two are equal with one another, we can say that 1 is equal to this, right? So we get 1 is equal to the probability of P plus the probability of not P. And by doing some handy-dandy rearranging, we can conclude that the probability of not P is equal to 1 minus the probability of P. Here's another useful consequence of Kolmogorov's axioms. In general, whether or not P and Q are incompatible or mutually exclusive, the following holds. General additivity. The probability of P or Q is equal to the probability of P plus the probability of Q minus the probability of P and Q. The proof of this from the axioms is slightly involved, so we're not going to cover it here. It's actually much easier to see why it must be true by inspecting a Venn diagram. So in a Venn diagram like this, we take the points in a circumscribed plane to represent all logically possible worlds, and then we use sets of points to represent sets of possible worlds, and in particular to represent all those possible worlds where some proposition P is true, or where some proposition Q is true. The areas of these spaces can then be used to represent the probabilities of the relevant propositions. In this diagram here, the proposition P or Q corresponds to the points which are either in the area labeled P, or in the area labeled Q, or in both. And the proposition P and Q corresponds to the points which are in both the area labeled P and the area labeled Q. So that's going to be this cross-hatched area here. It's pretty easy to see that if we tried to work out the area corresponding to P or Q by simply adding the area for P to the area for Q, well, then we would count the cross-hatched area twice, right? If we add this whole circle to this whole circle, we will have counted this cross-hatched area twice. We'll have double counted it. So to get the right answer for the probability of P or Q, we need to correct that double counting by subtracting the cross-hatched area. And of course, that cross-hatched area is just the probability of P and Q. And so we get that the probability of P or Q is equal to the probability of P plus the probability of Q minus the probability of P and Q. Because again, when we look at the diagram, we see that simply adding the probability of P to the probability of Q would count the probability of P and Q twice. And so to get the probability of P or Q, we need to correct that by subtracting out the probability of P and Q. In some cases, the probability of P and Q will be 0, namely when P and Q are incompatible, and so then there won't be a cross-hatched area. Their Venn diagrams won't overlap at all. And in that case, the probability of P or Q will be the simple sum of the probability of P and the probability of Q, as in Kolmogorov's third axiom. And general additivity applies in that case, right? It's just that the probability of P and Q in that case is 0, because if P and Q are incompatible, well then obviously it cannot be the case that P and Q, that's a contradiction. And so it has a probability of 0. And so when P and Q are mutually exclusive, we get that the probability of P or Q is equal to the probability of P plus the probability of Q. And if you remember, that's just finite additivity. So here are some other pretty important consequences of Kolmogorov's axioms. We won't derive them here, but they're important to note nonetheless, and I just want to say something to their intuitiveness. So one is maximality, which says that for any proposition P, the probability of P is less than or equal to 1. Together, non-negativity and maximality establish the bounds of our probability scale, right? Remember, non-negativity just says that probabilities are non-negative. They're going to be greater than or equal to 0. Maximality, by contrast, says that probabilities are less than or equal to 1. So now we have bounds for our probability scale. Probabilities, which again you can helpfully think of them for present purposes as rational credences, probabilities always fall between 0 and 1 inclusive. Now, this upper bound is kind of arbitrary, of course, but using 0 and 1 lines up nicely with everyday talk of being 0% confident or 100% confident in particular propositions, and also with various considerations of frequency and chance, so it's useful. Another consequence of Kolmogorov's axioms is contradiction. For any contradiction F, the probability of F is 0. One way to see that just intuitively is that a contradiction is just the negation of a tautology, and a tautology has a probability of 1, and we already saw that the probability of not P equals 1 minus the probability of P, which means that the probability of a contradiction is going to be 1 minus the probability of a tautology, which is just 1 minus 1, which is just 0, goose egg, nada, zilch. But anyway, it also makes sense. A contradiction is logically guaranteed to be false. There's literally no way it could be true, so its probability is 0. Another consequence is entailment. This says that for any propositions P and Q, if P logically entails Q, then the probability of P is less than or equal to the probability of Q. Right, so think about this one. Right, if P logically entails Q, well then any world in which P is true is also a world in which Q is true. So Q occupies at least as much of the possibility space as P. And Q must therefore be at least as probable as P. Q would be more probable, of course, if there are worlds in which Q is true while P is false, for then the worlds in which P is true will be a proper subset of the worlds in which Q is true. So anyway, I hope this is kind of intuitive on its face, but you can also think about it in Venn diagram terms. So you can imagine little boxes around these that represent the total space of possible worlds, but I was kind of lazy, I didn't want to put those in. You could just imagine the boxes there, and these are 3 separate Venn diagrams. And these Venn diagrams are representing the relationship between P and Q. In this first diagram, the set of logically possible worlds in which Q is true is a subset of the set of possible worlds in which P is true. Editing Joe here now. More precisely, the set of possible worlds in which Q is true is a proper subset of the set of possible worlds in which P is true. I think I also go on to say that P in this third Venn diagram is a subset of the set of possible worlds in which Q is true, but I should have clarified that, more precisely, it's a proper subset. Alright, back to the video. In this case, P and Q are logically equivalent, they're true in exactly the same worlds. And in this case, the worlds in which P is true are a subset of the worlds in which Q is true. If P logically entails Q, well then this one cannot be the case. This cannot be a representation of the situation that we have, right? Because remember, if P logically entails Q, then any world in which P is true is also a world in which Q is true. But that's not the case on this diagram, right? Like, pick a world that's like right here, where my cursor is. Well, that's a world in which P is true, but in which Q isn't true, because this is outside the circle for Q. And so this represents a case where P does not logically entail Q. By contrast, in both of these cases, any world in which P is true is indeed also a world in which Q is true. And so these are the only 2 candidate representations of the case that we have when P logically entails Q. But notice that in both of these cases, the probability of P is less than or equal to the probability of Q. In this case, the probability of P is equal to the probability of Q. They take up the exact same amount of the possibility space. And in this case, the probability of P is less than the probability of Q. And so look, we've just shown it visually that if P logically entails Q, then the probability of P must be either less than or equal to Q. Finally, think about this one in everyday terms, right? Compare the proposition that John has a dog with the proposition that John has a female dog with white fur, 4 brown spots, a curly tail, floppy ears, and brown eyes. Which of these is more probable? Well, clearly the first is more probable, right? The reason is that the second entails the first, but the first doesn't entail the second. The first is, in that sense, more modest. It could be true even while the second is false. It doesn't demand as much of reality. So the first is going to be more probable than the second. Alternatively, you can think of this in terms of ways of being false. Any way for this first claim to be false is also a way for this second claim to be false. But there are indeed ways for the second to be false while the first is true. So for instance, John could have a dog even though his dog is male, or even though it has brown fur, even though it has 5 brown spots, even though it doesn't have a curly tail, etc. So there are more ways, in principle, for the second claim here to be false than for the first to be false. And so the second is going to be less probable than the first. There are more ways, in principle, for the second to be false, and so it's going to be less probable. Now again, in this example, the first claim entails the second, while the second claim does not entail the first. If you have mutual entailment between the propositions, well then we get the next consequence of Kolmogorov's axioms, which is equivalence. This says that for any propositions P and Q, if P logically entails Q and Q logically entails P, well then the probability of P equals the probability of Q. And this makes perfect sense, right? Any way for one of the propositions to be false is also a way for the other to be false, and moreover, any way for that one to be false is also a way for the first one to be false. You can't find any world in which one is true while the other is false. So they're true in exactly the same worlds. They're equiprobable. It's literally impossible for there to be a case in which one of them is true while the other is false. And if you think about this in Venn diagram terms, their Venn diagrams are going to perfectly overlap one another. And also just notice that equivalence is a consequence of entailment. Right? If P logically entails Q, then the probability of P is less than or equal to the probability of Q. And by the same token, if Q logically entails P, then the probability of Q is less than or equal to P. And when you have A is less than or equal to B, but also B is less than or equal to A, it just follows from that A and B are equal to each other, right? Just think about that. A further important consequence of Kolmogorov's axioms is finite additivity extended to any finite set of mutually exclusive propositions. So this says that for any finite set of mutually exclusive propositions, P1, P2, through Pn, The probability of the disjunction of those propositions is just equal to the sum of the probabilities of those individual disjuncts. And this is basically just general additivity extended to cover any finite set of mutually exclusive propositions, rather than just a two-membered set. Now, you might be wondering, Joe, okay, these axioms are cool and all, but, what's so irrational about flouting them? Who cares if I flout these normative constraints on credences? So what if my credence in P is 0.6, while my credence in not P is also 0.6? What are you going to do about it? Well, of course there's nothing in psychology that rules out the possibility that an agent at a time might attach a credence of 0.6 to, say, the proposition that it'll rain tomorrow, and simultaneously a credence of 0.6 to the proposition that it won't rain, thus violating the immediate implication of the probability axioms that the probability of P equals 1 minus the probability of not P. So yeah, there's nothing in psychology that rules that out. But in addition to it's just being seemingly self-evident that that's irrational, set that self-evidence aside, in addition to that seeming self-evidence, there's an argument that any rational credences must conform to the axioms of probability, even if someone's actual credences don't always do so. And the argument is that anybody whose credences violate the axioms of probability can have a Dutch book made against them. A Dutch book is a set of bets which guarantee that you'll lose money no matter what outcome occurs. So by way of illustration, consider the person whose credence that it will rain is 0.6 and whose credence that it won't rain is also 0.6. Well, this person will happily pay 60 cents to win $1 on its raining, and also will happily pay 60 cents to win $1 on its not raining. They'd be willing to make those bets. Those bets are perfectly fair by their lights. But anybody who makes this pair of bets will be guaranteed to lose money no matter what happens, whether it rains or not, because they'll have paid out $1.20 in total, and will only win $1 whether or not it rains, right? It's either going to rain or it's not. If it rains, they're only going to be making $1, and if it doesn't rain, they're going to be making $1. And yet they'd be willing to pay 60 cents on both of these bets. And so they'd be willing to pay out $1.20, even though they can only win $1 in this situation. And so they're guaranteed to lose money here. And in general, it's not that hard to prove that a Dutch book can be made against you just in case your credences fail to satisfy the axiom of probability. And since it seems clearly irrational to adopt attitudes that make it certain that you will incur a loss, it follows that any rational agent will have degrees of belief that do conform to the probability calculus. And that also includes Bayes' theorem, by the way, because that's a consequence of the axioms of probability theory. There are other reasons for thinking that these axioms normatively constrain credences. So there are, for instance, accuracy-based approaches to arguing for these rational constraints. That basically has to do with how well you're doing getting at the truth, and we basically assess your credences in terms of how close they are to the truth. It turns out that by your own lights, you maximize your chances of getting to truth if you obey the probability axioms. So anyway, there are accuracy-based approaches to arguing for these rational constraints, and there are lots of other approaches besides, but we're not going to get into that here. That's a huge literature unto itself. We've covered the Kolmogorov's axioms enough. So now we're going to be turning to the fourth rational constraint on credences, or the fourth core normative rule of Bayesian epistemology. And that is the ratio formula. Yes, indeed. So again, the ratio formula is the fourth core normative rule of Bayesian epistemology. Before getting into it, though, we need to get clear on conditional probability. A conditional probability is the probability of one proposition being true on the assumption of another proposition being true. It's the probability that one proposition is true given that another proposition is true. And we represent the probability of P conditional on Q as the probability of P given Q. It's this little thing on screen here. This says the probability of P given Q. Okay, so again, this is the probability of P given that Q is true, or on the supposition that Q is true, or assuming that Q is true, or on the condition that Q is true. Okay, you get it. Oh, and by the way, an unconditional probability is just a probability that isn't conditional. So yeah, that is an unconditional probability there. It's not conditional on anything, but alas, we introduced the conditional back because that's how the slide was originally. All right, with that out of the way, here is the ratio formula. The ratio formula says that for any propositions P and Q, the probability of P given Q equals the probability of P and Q divided by the probability of Q, where, of course, the probability of Q is greater than 0 because you can't divide by 0. That is undefined. So that's a bit abstract, and it might be hard to see on its face why it would be true. And that's where handy-dandy Venn diagrams come in. So consider the following Venn diagram. Again, the rectangle itself is going to be representing all logically possible worlds. The probability of P is the fraction of that rectangle taken up by the P circle. And by the way, the area of the rectangle is stipulated to be 1. And so the fraction of the rectangle taken up by the P circle is just the area of the P circle divided by 1, which of course is just the area of the p circle. So yeah, the probability of p is the fraction of the rectangle taken up by the p circle. And the same thing goes for the probability of q. When we ask about the probability of a proposition conditional on the assumption that q, we temporarily narrow our focus to just those possibilities that make q true. Right? In other words, we exclude from our attention the worlds shaded in within this diagram. And we then consider only what's in the q circle. The probability of p given q is then the fraction of the q circle occupied by the p worlds. And so it's the area of the p-q overlap divided by the area of the entire q circle. And notice that that's just the probability of p and q divided by the probability of q. And that, of course, gives us the ratio formula, right? The probability of p given q is equal to the probability of p and q divided by the probability of q. I just want you to think about this intuitively, right? The probability of p given q, the probability of p on the assumption that q is true. Well, what do we do there? What do we do to assess that? Well, we narrow our focus to the worlds in which q is true, and then we ask, among the worlds in which q is true, what's the proportion of those in which p is also true? And notice that that just is the probability of p and q out of the probability of q, right? So it's the probability of p and q divided by the total probability of q. That is the probability of p given that q is true. I hope that that's intuitive. To give a concrete example, in the scenario in which I roll a fair die, the initial range of possibilities includes all 6 outcomes of the die roll. I then ask for the probability that the die comes up 6 conditional on its coming up even. That is the probability of 6 given that it's even. To assign this value, we exclude from consideration all the odd outcomes. Note that we haven't actually learned that the die outcome is even. We've simply been asked to suppose that it comes up even and assign a probability to other propositions in light of that supposition. We then distribute the probability equally over the outcomes that remain under consideration, which is 2, 4, and 6. And so the probability of 6, conditional on even, is 1 out of 3, 1/3. And of course, we get the same result from the ratio formula. The probability of 6 given E is equal to the probability of 6 and E divided by the probability of E. The probability of getting a 6 and even just is the probability of getting a 6, right? So that's 1/6. And then you divide that by the probability of even, which is of course 1/2. And 1/6 divided by 1/2 is 1/3. So importantly, the ratio formula allows us to calculate conditional probabilities from unconditional probabilities, that is, probabilities relative to no suppositions, beyond perhaps our background information. Again, keep in mind that the ratio formula is a rational constraint on how an agent's conditional credences should relate to their unconditional credences, and as a normative constraint rather than a definition, and as a normative constraint it can be violated by assigning a conditional credence that doesn't equal the specified ratio. And if you violate it, you'll be susceptible to a Dutch book. Anyway, onwards we march to the 5th and final core normative constraint on rational credence, and that is the conditionalization principle. So according to Bayesians, when you acquire new evidence, you should update your beliefs that the evidence bears on by conditionalization. So yeah, we have some hypothesis H that you have a certain credence in, and we also have information E, or evidence E, that you learn. According to the conditionalization principle, you should update your credence in H by conditionalizing on the new information E. And what that means is that when you learn new information E, your new probability of H, after learning E, should equal your old probability of H given E before you learned E. So that's what the new and the old represent. Your new probability of H, it's new insofar as it's after you learn E, and your old probability of H given E, it's old insofar as it's before you learn E. Also, we don't necessarily need to cast this in terms of learning, we could just cast it in terms of considering. Maybe you knew E all along, but never stopped to consider how E bears on some of your beliefs or some of your credences. So we could say when you newly consider information E within an epistemic context, your new probability of H should equal your old probability of H given E. So yeah, that's it. That's the simplest articulation I can muster of the conditionalization principle, or again, sometimes known as the principle of conditionalization. And by the way, obeying the conditionalization principle is often known as updating by conditionalization. And hopefully you find this pretty intuitive. Suppose you don't know whether it's raining or not right now. I ask you, hey, if it's raining right now, how likely do you think it is that it will still be raining in 2 hours? Suppose you answer, about 40%. And then you look outside and see that it actually is, in fact, raining, and that's all you learn. I then ask you, well, now how likely do you think it is that it will be raining in 2 hours? Well, if you're rational, you're going to answer 40%, right? If that isn't intuitively obvious, it's also possible to construct a Dutch book for anyone who fails to update by conditionalization, but we won't get into that here. So again, the conditionalization principle is a rational constraint on credences, and in particular, it's a rational constraint on credences across time. The Kolmogorov axioms and the ratio formula relate rational credences at a single time. They're basically rational demands on consistent and coherent credences at any given time. By contrast, conditionalization relates rational credences at different times. It requires rational credences to line up in a particular way across time, and the central idea is that rational agents should conditionalize whenever they gain new information. So anyway, that's basically the least formal way that I could have stated the principle, is that when you gain new information E, your new probability of H should equal your old probability of H given E. But I do want to give two slightly more formalized versions of the principle while still retaining accessibility. And to do that, I'll be continuing with concrete, tangible examples to make things as comprehensible as possible. Suppose that you have the following probability assignments, and again remember that we can helpfully treat probabilities as rational credences, at least for the purposes of this section. So the probability that Johnny goes to the party is 1/2, and the probability that Johnny goes to the party conditional on Jane's going to the party is 2/3. So yeah, suppose that those are your probability assignments. Well, now you learn that Jane is going to the party. The question then is, what should your new probability in Johnny's going to the party be? Well, the answer is obvious enough. It's 2/3, right? If it was right to think beforehand that the conditional probability of Johnny going on the assumption that Jane goes is 2/3, and if now it turns out that Jane really is going, well then it must be right to think that the new unconditional probability that Johnny goes has increased to 2/3. I mean, again, think of it in Venn diagram terms. You now know you are inside the area of the Venn diagram for Jane's going. And you have already decided that the proportion of this area that covers Johnny's going as well is 2/3. And so it must now be true that the probability of Johnny going is 2/3 after you learn that Jane is in fact going. You basically narrow your focus to the space occupied by Jane going, and your new probability that Johnny goes to the party is just equal to your old probability that Johnny goes given that Jane goes, which is just the proportion of this whole circle taken up by the cross-hatched area. Again, updating your credences in this kind of way is called conditionalization, and we can offer a slightly more formal version of the principle as follows. If your old conditional probability of P given Q is equal to X, and you come to know that Q is true, well then the new probability that P is true is equal to X. Notice here that Q needs to be understood as representing everything you come to know. The principle doesn't work if Q is only part of your new knowledge. To illustrate this, suppose that in the above example, you learn not only that Jane is going to the party, but also that she will be accompanied by Jill. And suppose that you had always thought that there was almost no chance that Johnny would go if both Jane and Jill did, right? You had, in other words, a very low old conditional probability that Johnny goes, conditional on the assumption that both Jane and Jill go. Even though your old probability that Johnny goes conditional on Jane going was 2/3. You can imagine that this little red circle represents the probability that Jill goes, and as you can see, the amount of overlap between Jill's circle, Jane's circle, and Johnny's circle is a super duper tiny fraction of the entire Jill circle. So here, the probability that Johnny goes, given that both Jane and Jill go, is super duper tiny. And so while it is still true that you have learned that Jane will go, it's no longer a good idea to attach a 2/3 probability to Johnny going, simply on the grounds that your old probability that Johnny goes conditional on Jane going is 2/3. And the reason that's not a good idea is precisely because you have learned more than that Jane will go to the party. You now know not just that you are inside Jane's Venn diagram, you now know not just that you are inside of Jane's circle, so to speak, but more specifically that you are inside of that bit of Jane's circle, which is also inside of Jill's circle, which is that bit of the probability space where Jill also goes to the party. And the proportion of that area, where Johnny goes in addition to Jane and Jill going, is very, very small indeed. So this just illustrates that when you're updating by conditionalization, you need to update on everything you come to know within the given time period. Finally, here's a still more formal version of the conditionalization principle. Still, though, I think it's relatively understandable. So the principle says that for any time t and later time t star, if proposition E represents everything an agent learns between t and t star, and if the agent's probability of E at t is greater than 0, then for any proposition H, the agent's probability of H at t star equals the agent's probability of H given E at t, where the p subscript t and p subscript t star are basically the agent's probability distributions at the two times. A probability distribution is basically just a way of assigning probabilities to different propositions within our propositional language. So yeah, these are basically just assignments of probabilities to different propositions indexed to a given time, and of course, relative to a particular agent. So we're talking about an individual agent's probabilities in certain propositions indexed to particular times, and how we represent that indexing is by subscripting the time, t star or t. So as you can see from this principle, conditionalization captures the idea that an agent's probability, or rational credence of h at t star after learning E, equals their earlier probability at t, right, equals their earlier probability in h had the agent merely supposed that E is true. So their later probability in h after learning E is equal to their earlier probability of h given E. And when an agent updates their credence distribution by applying this principle of conditionalization to some learned proposition E and some hypothesis H, we say, again, that the agent conditionalizes on E. That's what Bayesians are saying when they talk about conditionalizing on some evidence. Keep in mind, again, and I emphasize this because it is very often overlooked, this is a rational constraint. An agent's actual credences may not obey the conditionalization principle, like an agent's actual credences might not satisfy this. The point is that if the agent is being rational, then their credences obey this. Now, the conditionalization principle is especially relevant to Bayes' theorem, since Bayes' theorem offers us a way to calculate the probability of h given E, and in particular to calculate an individual agent's probability of h given E at time t. So the conditionalization principle, together with Bayes' theorem, provides for us the rational way to update our beliefs and credences, as well as to confirm or disconfirm our theories and hypotheses in light of new evidence, in light of new data. This is the ultimate significance of Bayes' theorem and these various normative constraints on rational credence. This is the rational way to update your beliefs, to update your credences, to confirm or disconfirm theories, hypotheses, etc. That is the broader significance of all this. Now, that would be a perfect bridge into Bayes' theorem itself, but there's one final distinction within Bayesian epistemology that you should be aware of before we get into the almighty theorem, and that's the distinction between subjective and objective Bayesianism. So there are different ways to articulate the distinction between subjective and objective Bayesianism, but a central way to delineate them, and this is sometimes called the normative distinction between subjective and objective Bayesianism, a central way to delineate them is in what rational constraints they put on credence. The subjective Bayesian basically stops at the 5 core normative rules that we've just been over, together of course with whatever's entailed by them, such as Bayes' theorem itself. Objective Bayesians, by contrast, put further rational constraints on credence. As a result, for the subjective Bayesians, there is no one uniquely rational response to a set of evidence. It all depends on your initial credences in the propositions involved, or your prior probabilities in the various hypotheses, sometimes called your priors. As long as your priors satisfy the axioms of probability, as long as they meet those relatively minimal coherence conditions and like being within 0 and 1 and those sorts of things, and of course, as long as you update by conditionalization and obey the ratio formula, you're going to count as perfectly rational for the subjective Bayesian. The main objection to subjective Bayesianism is that, of course, it's too subjective. For instance, you might think that, in light of all the evidence we currently have, it's simply not rational to think that the Earth rests on the back of a giant pink turtle. That just isn't a possible justified response to our current evidence, you might think. But on the subjective Bayesian view, it is a possible justified response to our evidence, right? All you have to do is assign a super-duper high prior probability to that sort of turtle cosmology, high enough that it will sufficiently outweigh even the mountains of evidence that we have against this turtle cosmology. In essence, then, subjective Bayesians think that a rational belief is just a belief that doesn't violate any of the 5 core normative constraints on rational credence. And it's not that difficult to assign a super-duper high prior probability in what otherwise seems to other people to be a very implausible theory, while nevertheless respecting all of those core normative rules. Other philosophers, however, think that rationality is more demanding, and these people fall into the objective Bayesian camp. Objective Bayesians think there are substantial additional constraints on rational credences, beyond the Kolmogorov axioms, the ratio formula, and the conditionalization principle. One of the main motivations for this, again, is to avoid excessive subjectivity and to put stricter constraints, especially on one's prior probabilities in various hypotheses. One of those additional constraints might be the principle of indifference, for instance, which basically says that if there are no reasons favoring A over B or B over A, then the probability of A is the same as the probability of B. There are other candidates for additional constraints on rational credence, and there's a lively debate about the principle of indifference, but you get the point. Objective Bayesians add further rational constraints. I just wanted to give you a sense of this distinction between subjective and objective Bayesians before moving on, since it's important for understanding the broader framework of Bayesian epistemology. Alright, we're finally onto the theorem itself! Woohoo! So yes, the most famous consequence of the ratio formula and Kolmogorov's axioms is Bayes' theorem. For any propositions h and e, the probability of h given e is equal to the probability of e given h times the probability of h divided by the probability of e. We can label h and e as a and b or p and q or whatever we want. For present purposes, I did it in terms of h and e because Bayes' theorem is typically used to talk about the confirmation or disconfirmation of various hypotheses in light of evidence or data. So sometimes you'll also see d used, but e is more often used. Also, part of Bayes' theorem is the stipulation that the probability of e is greater than 0, because, of course, you can't divide by 0. So the first thing to say about Bayes' theorem is just a reminder that it is indeed a theorem. It can be proven straightforwardly from the Kolmogorov axioms together with the ratio formula. We'll actually go through a relatively simple proof of Bayes' theorem in a second. But before that, I want to briefly talk through the terms used in this formula. So again, strictly speaking, h and e are just going to be propositions, but when we're talking about Bayesian epistemology, we're really concerned with hypotheses and evidence. So going forward, we're going to be treating e as some piece of data or evidence. We're going to be treating h as some hypothesis. The probability of h given e is the posterior probability of h. It's the probability of h posterior to considering e. The probability of e given h is what's often called the likelihood, or sometimes the likelihood of h. I know that's unfortunately named because likelihood sounds like probability, so it sounds like you're talking about the probability of h, but no, when we're talking about likelihoods, we're talking about the probability of pieces of evidence given hypotheses. So you can think of it as the probability or the likelihood that e would be true conditional upon the truth of h. The probability of h is the prior probability of h, that is the probability we assign to h prior to considering the piece of evidence e, and then the probability of e is just, of course, the probability of the evidence itself. It's a probability that the evidence itself would be true at all. It's a probability that the evidence itself would be true or would obtain at all. Now, regarding the prior probability of h, don't confuse prior probabilities with intrinsic probabilities. The prior probability of h means the probability that h is true before considering some specific item of evidence, but usually after encountering other items of evidence. By contrast, the intrinsic probability of h is the probability that h is true before considering any evidence whatsoever. It's determined solely by the content of h itself, without taking into account any evidence for or against h. Paul Draper offers a plausible theory of intrinsic probabilities, according to which they depend on the modesty and coherence of a hypothesis. A hypothesis is modest to the extent that it does not commit us to saying very much about the world. Modesty is thus a measure of how much the hypothesis asserts. The more a hypothesis claims, the more ways there are in principle for it to be false, and, as a result, the less likely it is to be true, prior to looking at any evidence, that is. A hypothesis is coherent to the extent that its conjuncts or elements cohere well with each other. They fit together well, or they raise, or at least don't lower each other's probabilities. So think of coherence as a measure of how well the various parts of a hypothesis fit together. If the different parts count against each other, if, conditional on one of the parts being true, the other parts are unexpected or unlikely, well then the hypothesis is less coherent and thus less likely to be true. So yeah, just keep these notions distinct in your mind. Intrinsic probability refers to the probability of the hypothesis independent of any and all evidence we have for or against it, whereas prior probability may very well take into account various pieces of evidence that you've conditioned on in the past. Prior probability, again, is simply the probability of the hypothesis prior to looking at some particular item of evidence under consideration. So we've got the theorem here, but we can ask, how do we know that Bayes' theorem is true? And the answer is because we can prove it. In fact, we can prove it in several ways, and I'm just going to give what I think is the most intuitive and the easiest and the simplest way to see why it's true. So recall the ratio formula. For any propositions p and q, the probability of p given q equals the probability of p and q divided by the probability of q. Notice that this holds for any p and q, and so we can get one instance of the ratio formula by first plugging in h for p and e for q. And then we can get a second instance of the ratio formula by plugging in e for p and then h for q. So when we plug in h for p and e for q, we get 1 here. The probability of h given e is equal to the probability of h and e divided by the probability of e. So look, we're plugging in h for p, and we're plugging in e for q. And as I just said, we can also plug in e for p and h for q, right? So that's just what 2 is. This follows from the ratio formula. It's the same thing as the ratio formula, but you're just plugging in e for p and then h for q. So we've got the first 2 steps of our proof. Let's then do some rearranging. The probability of h given e times the probability of e equals the probability of h and e. This follows from 1. Look, all you have to do to get from 1 to 3 is just multiply each side by the probability of E. When you multiply this side by the probability of E, the probability of E's cancel out, and then you're just left with the probability of H given E times the probability of E equals the probability of H and E. You're moving the probability of E from the denominator over here to the left side of the equation. And we can also do some more rearranging. We're doing basically the exact same thing to premise 2, right? We're multiplying both sides of the equation in premise 2 by the probability of H. And when you do that, you get the probability of E given H times the probability of H, and so we get our next 2 steps of the proof. But notice that the probability of H and E is equal to the probability of E and H. Now, I hope that this step is just intuitively obvious on its face, right? I mean, obviously, like, the probability that it rains and it's Tuesday is just the same as the probability that it's Tuesday and it rains. Like, this step should be obvious. But also note that this step follows from the fact that H and E is logically equivalent to E and H, together with the consequence of Kolmogorov's axiom known as equivalence, which we went over earlier in the video. For any propositions P and Q, if P logically entails Q and Q logically entails P, then the probability of P equals the probability of Q. So given that H and E is logically equivalent to E and H, and what that means is that they each logically entail the other, and that just follows from the truth conditions for this logical connective for conjunction. And so given that they're logically equivalent, and so each logically entails the other, it follows from equivalence that their probabilities have to be the same as well. And then from 3 through 5, it follows that the probability of H given E times the probability of E equals the probability of E given H times the probability of H. Right? Notice what 5 is saying. It's saying that the probability of H and E, which shows up here, is equal to the probability of E and H, which shows up here. Right? So given that these two are identical with each other, and that the top one here is identical to this, and the bottom one here is identical to this, well, then these two have to be identical with one another as well, right? We know that these two are identical from 5, and so it follows that these two are identical. That is what 6 is saying. It's saying that the probability of H given E times the probability of E equals the probability of E given H times the probability of H. That's just what 6 says. And finally, it's then just a straightforward step from there to get to Bayes' theorem. Look, all you have to do is divide both sides by the probability of E. When you divide this side by the probability of E, the probability of E's cancel out in the numerator and the denominator, and then on the right-hand side, you're left with the probability of E in the denominator. So we get Bayes' theorem. The probability of H given E equals the probability of E given H times the probability of H divided by the probability of E. Now, I know it sounds kind of complicated going through that here, but if you think about it, it's actually quite simple, right? We just have 2 instances of the ratio formula, and we have an instance of equivalence. The rest just logically follows. And the rearrangements aren't all that complex. Usually we're just dividing both sides by a term or multiplying both sides by a term. So anyway, I hope that this proof was illuminating for you and helps you see why Bayes' theorem follows from Kolmogorov's axioms in the ratio formula. Now, I do want to show a 3 blue, 1 brown video to illustrate the simplicity of this kind of proof. So let's get on to that next.
If your goal is simply to understand why it's true from a mathematical standpoint, there's actually a very quick way to see it based on breaking down how the word "and" works in probability. Let's say there are 2 events, A and B. What's the probability that both of them happen? On the one hand, you could start by thinking of the probability of A, the proportion of all possibilities where A is true, then multiply it by the proportion of those events where B is also true, which is known as the probability of B given A. But it's strange for the formula to look asymmetric in A and B. Presumably, we should also be able to think of it as the proportion of cases where B is true, among all possibilities, times the proportion of those where A is also true, the probability of A given B. These are both the same, and the fact that they're both the same gives us a way to express P of A given B in terms of P of B given A, or the other way around.
And also, I just want to pause at this point and say that this right here is basically just the ratio formula. Right? Remember the ratio formula. It said that the probability of A given B is equal to the probability of A and B divided by the probability of B. But that's just a rearrangement of this equation here. All you have to do is divide both sides by the probability of B. So if you take this probability B and put it over here in the denominator, then you get the ratio formula. So this is just an alternative way of expressing the ratio formula. That's what I'm trying to emphasize here.
So when one of these conditions is easier to put numbers to than the other, say when it's easier to think about the probability of seeing some evidence given a hypothesis rather than the other way around, this simple identity becomes a useful tool. And you know, while we're here, it's worth highlighting a common misconception that the probability of A and B is P of A times P of B. For example, if you hear that 1 in 4 people die of heart disease, It's really tempting to think that that means the probability that both you and your brother die of heart disease is 1 in 4 times 1 in 4, or 1 in 16. After all, the probability of 2 successive coin flips yielding tails is 1/2 times 1/2, and the probability of rolling 2 ones on a pair of dice is 1/6 times 1/6, right? The issue is correlation. If your brother dies of heart disease, and considering certain genetic and lifestyle links that are at play here, your chances of dying from a similar condition are higher. A formula like this, as tempting and clean as it looks, is just flat out wrong. What's going on with cases like flipping coins or rolling 2 dice is that each event is independent of the last. So the probability of B given A is the same as the probability of B. What happens to A does not affect B. This is the definition of independence. Keep in mind, many introductory probability examples are given in very gamified contexts, things with dice and coins, where genuine independence holds. But all those examples can skew your intuitions. The irony is that some of the most interesting applications of probability, presumably the whole motivation for the kind of courses using these gamified examples, are only substantive when events aren't independent. Bayes' theorem, which measures exactly how much one variable depends on another, is a perfect example of this.
Now, you won't always see Bayes' theorem like this. Sometimes you'll see it instead as this. For any h and e, the probability of h given e is equal to the probability of e given h times the probability of h, divided by the probability of e given h times the probability of h, plus the probability of e given not h times the probability of not h. That's a mouthful. Now, these two are actually equivalent because those denominators are equivalent, right? Like, notice that the numerators are exactly the same, and these denominators are actually equivalent. The more complicated denominator just offers a fleshed out way to calculate the probability of E. So here is why these two are identical. And this is probably going to be the most technical part of the video. I'm going to try my hardest to make this as accessible as possible, but I want to give you guys a really deep understanding of Bayes' theorem. And so I want you guys to see why these two are equivalent. I want you to have a deep, unifying, explanatory understanding of Bayes' theorem. And because of that, I want to show you that these two are identical. I don't want you to just take my word for it. So we want to show that the probability of E equals the probability of E given H times the probability of H, plus the probability of E given not H times the probability of not H. For starters, I hope this is perhaps somewhat intuitive on its face. Like, the probability that I go on a run is equal to the probability that I go on a run assuming that it's raining, times the probability that this assumption is correct, plus the probability that I go on a run assuming it's not raining, times the probability that that assumption is correct. Right, like it's either raining or it's not raining, and conditional on it's raining, there's a certain probability that I go running, and conditional on it's not raining, there's a certain probability that I go running. And so you can go down each of those horns of the dilemma, and then find the probability that I run given that horn of the dilemma, times, of course, the probability that that horn would obtain at all, and then just add that to the probability that I'd run on the other horn of the dilemma, times, of course, the probability that that horn is itself true. So I'm hoping that that verbal walkthrough can at least make this intuitively plausible to you, but there is a more formal way to see why they're the same, and if you're like me, you're not going to settle just for that kind of reasonably intuitive understanding. You want to go deeper. So here's a more formal way to show that these two are the same. Bam! Okay, so I'm going to talk through this, but this only has 6 steps, and the first step is quite convoluted. But what I'm going to do is I'm going to give you a bird's eye overview of the proof here. And so I'm just going to go through steps 1 through 6, and then I'll explain why we know that step 1 is true. So step 1 says that E is logically equivalent to the following disjunction. This is a disjunction of 2 disjuncts. The first disjunct is E and H, and the second disjunct is E and not H. So what this is saying is that E is logically equivalent to E and H, or E and not H. And so once you just spot me that, and I'm going to prove that in a second, but once you spot me that, it follows by equivalence that the probability of E equals the probability of E and H or E and not H. Right, remember, by equivalence, if P is logically equivalent to Q, that is, if P logically entails Q and Q logically entails P, well then the probability of P equals the probability of Q, right? And since E is logically equivalent to this, it follows that the probability of E is equal to the probability of this. So 2 follows from 1 together with equivalence. But notice that E and H on the one hand, and E and not H on the other are incompatible. These can't both be true, right? It can't both be true that E and H as well as E and not H, because then both H and not H would be true, and that's contradictory. So these two are incompatible with one another. And remember, by finite additivity, whenever you have a disjunction of mutually incompatible disjuncts, it follows that the probability of that disjunction as a whole is just equal to the sum of the individual probabilities of the individual disjuncts. So 3 follows from finite additivity, but notice what we have in 2 and 3. Here we have probability of this disjunction, and here we have the probability of that very same disjunction. And we have equal signs, so we have the probability of E being equal to the probability of this disjunction, and the probability of this disjunction being equal to the probability of E and H plus the probability of E and not H. And from those, it just follows that the probability of E is identical to the probability of E and H plus the probability of E and not H. We have here the structure A is equal to B and B is equal to C, and from that it follows that A is equal to C, right? So from 2 and 3, we get that the probability of E equals the probability of E and H plus the probability of E and not H. But remember, by the ratio formula, the probability of E and H is equal to the probability of E given H times the probability of H. This is again that same rearrangement of the ratio formula. As I originally articulated it, the probability of H was over here in the denominator, but it's the same thing, right? We just multiply both sides by the probability of H. And remember, you can apply the ratio formula to any propositions P and Q. So we have it both being the case that the probability of E and H equals the probability of E given H times the probability of H, and the probability of E and not H is equal to the probability of E given not H times the probability of not H. And notice again that here, this term here is equal to this term here, and so we can just plug this into this above equation here. And notice that this term here is equal to this term here, and so we can plug in this for this term here. And so then from 4 and 5, it follows that the probability of E equals the probability of E given H times the probability of H plus the probability of E given not H times the probability of not H. And that's precisely what we wanted to prove. Okay, I understand that that's a bit technical, but that's the bird's eye view. And so we can prove that these two are equivalent, given that you spot me this first thing, that E is logically equivalent to E and H or E and not H. And so my task now is to prove that this is, in fact, logically equivalent to this. And to do that, what I'm going to do is we're going to suppose that E is true and then show that this follows. And then we're going to suppose that this is true and then show that E follows. And so that'll show that kind of bidirectional entailment. It'll show that E logically entails this, and it'll also show that this logically entails E, and hence that they're logically equivalent. So let's go from the left to right direction, the logical entailment there. We're going to suppose that E is true, and then we're going to conclude from that supposition that this is true. And when you suppose something to be the case, and you prove another thing to be the case, well then you're licensed to say that, well then, if the first is the case, then the second is the case. So suppose that E is true, and remember, we're going to try to derive this disjunction. So suppose E is true. Well, either H is true or not H is true. Let's go under each horn of that dilemma. Suppose that H is true. Well then obviously, both E and H are true, right? We suppose that E is true, and now we suppose that H is true, and so E and H follows. But whenever you've proved something, you can add whatever you want in there to a disjunction, right? If you prove that snow is white, well then it follows from that either snow is white or Cinderella exists, or either snow is white or 1 + 1 = 7. That disjunction as a whole is true because at least one of its disjuncts is true, namely the first one. So under this horn of the dilemma, we were able to prove this disjunction. What about the other horn of the dilemma? Well, when we suppose that not H, we can conclude that E and not H, right? Because we're still under the assumption that E is true, and we just suppose that not H is true, and so it follows that E and not H is true. But then, again, we're able to introduce another disjunct into that because we've just proved this disjunct, so any disjunction with this as a disjunct is going to be true as a whole. And so this disjunction as a whole follows. So, whichever horn you pick, the disjunction follows. And whenever it's the case that either A or B, and whichever way you go, C is the case, well then you can just conclude that C is the case, right? So since under each horn of the dilemma, you get this disjunction, it follows that we could just conclude that disjunction. Right, like think about this more generally. If it's either the case that I go to the park or I don't go to the park, and either way I'm going to be happy, well then it just follows that I'm going to be happy. If I go to the park, I'm going to be happy. If I don't go to the park, I'm going to be happy. Well, since either I'm going to the park or I'm not going to the park, and since each of those entails me being happy, we can conclude that I'm going to be happy. And so we conclude that the disjunction itself is true. And notice what we've just done, right? We suppose that E is true, and we derive the disjunction itself. And so we can say that if E is true, then the disjunction follows. If I suppose that John is a bachelor, and then I derive from that supposition that John is male, well then I can just conclude that if John is a bachelor, then John is male. So now we've just proved the left to right direction. Next up, we want to prove the right to left direction. So we want to show how this disjunction logically entails E. And again, to do that, we're just going to suppose that the disjunction as a whole is true, and then we're going to ultimately derive E. And so then we're going to conclude that if the disjunction is true, well then E follows. Oh, and by the way, there should be one more parentheses here and here. Okay, I just did some makeshift editing to put little tiny parentheses there. Okay, so yeah, we're doing the right to left direction now. We're going to show how this disjunction entails E. So we're going to suppose that the disjunction is true, and then we're going to show how E follows from the disjunction. So suppose that the disjunction is true. Well, what we're going to do to show how E follows from that is we're basically just going to show that E follows from each of the disjuncts, right? Because again, whenever you have a disjunction, and you can show that each of the disjuncts entails something, well then you can just conclude to that something, right? So let's suppose that this disjunct is true, E and H. Well, obviously, if E and H is true, well then E is true. So we just showed that E follows from this disjunct. Well, does E follow from this disjunct? Well, of course it does, right? Suppose that E and not H is true, well then obviously E follows, right? So under either horn of this dilemma, E follows. And so since the disjunction as a whole is true, and since either horn of the dilemma entails E, we can conclude that E. But look what we just did, right? We suppose that the disjunction as a whole is true, and now we just derived from that E is true. And so we can say that if the disjunction is true, then E follows. So we say, if the disjunction is true, then E follows. And notice now that we've shown the right to left side of the logical equivalence. We've shown that this disjunction logically entails E. So we can put the little biconditional arrow here, and we've shown precisely what we wanted to show, that E is logically equivalent to the disjunction of E and H, or E and not H. Okay, all right, take a deep breath. I can promise you that was the most technical part of this video. Apologies if I lost you. I tried explaining this as best as I could, but yeah, that is probably the most technical part of this video. But again, the goal of this video, the goal of Majesty of Reason, is not to back down from those challenges. It's to rise up to the challenges. It's to exhibit that kind of intellectual perseverance, the intellectual curiosity, the intellectual responsibility to find out these things for yourself, to see why the probability of E is equal to the probability of E given H times the probability of H plus the probability of E given not H times the probability of not H. Okay, so anyway, think of this as an exercise in cultivating the intellectual virtues. That's what you're getting with the Majesty of Reason experience. You're not only getting philosophy, but I'm trying to build up your intellectual virtues along the way. Still, you might be thinking, like, okay, Joe, I get it. That's a lot of math and logic, but, like, what's the point? To what end? Well, what's the point of anything, honestly? No, okay, we're not getting into that topic here. The point, the significance, is one I've already mentioned. Bayes' theorem gives us a way to calculate the posterior probability of a hypothesis conditional on evidence. Together with the conditionalization principle, this gives us a recipe for rationally updating our credences and for confirming or disconfirming hypotheses, that is, increasing or decreasing their probability as a result of data. Here are some other important points pertaining to Bayes' theorem. So, we want to know how likely our hypothesis is in light of evidence E. That's given by the probability of H given E. So if we learn that E is true, we should revise our confidence in H by changing it from the probability of H to the probability of H given E, per the conditionalization principle that we went over. Looking at the right-hand side of Bayes' theorem, we can see that three things determine the probability of H given E, under this form of Bayes' theorem, what we could call the standard form. First, the probability of H given E is proportional to the prior probability of H itself. In other words, how likely H was to be true before we learned E, or how likely we would say H was if we didn't know E. The more probable the hypothesis starts out, the more probable it ends up. This also supports the slogan, extraordinary claims require extraordinary evidence, in the sense that if we have a hypothesis that is super implausible to begin with, then we're going to need significant evidence before the hypothesis becomes believable. Whereas if you started out with a pretty plausible hypothesis, not as much or not as strong evidence is needed for believability. Second, it's generally quite good if the likelihood of H, the probability of E given H, is high, right? That's generally quite good if that's high. Intuitively, if you want to support a theory, you want the theory to strongly predict some possible evidence, where the evidence then occurs. To strongly predict something is to imply that that thing is quite likely. At the very least, you want your hypothesis to predict the data better than the alternative hypotheses, but we'll talk about that more when we get to the odds form of Bayes' theorem and when we get to evidence. Right now, we're just speaking in general terms. Third, in general, it's pretty good if the probability of E is low, right? You can see from the theorem that as the probability of E goes down, the probability of H given E goes up, right? Whenever you divide by something, the smaller the denominator, the larger the resulting quantity as a whole is. So yeah, it's generally quite good if the probability of E is low, because as the probability of E goes down, the probability of H given E goes up. Combining this with the previous point, we can say that ideally and generally, you want a theory that strongly predicts evidence that is otherwise highly unlikely. You want E to be much more likely if H is true than otherwise. That's a straightforward path to a very strong confirmation of the hypothesis in question. But alas, I'm getting ahead of myself because I've got a whole section of this video dedicated to confirmation and evidence, and I'll speak in much more precise terms there rather than the general terms I've been doing here. So anyway, that's the standard form of Bayes' theorem, or the standard forms, again, two different ways that you can articulate it. But there are other forms of Bayes' theorem. The odds form is one of the most useful, and it's definitely my favorite. It's basically like my baby. I feed it, I nourish it, I pat it, it spits on me, it calls me daddy. I need to stop. It's pretty useful because when we're doing the calculations, we don't need to worry about the probability of the evidence or data, right? Notice that P of E doesn't show up anywhere in here. Instead, we simply worry about the prior probabilities of H and not H, as well as how well each of H and not H predict the data. That is, how likely they each render E. So yeah, here is the odds form of Bayes' theorem. It's on screen here. The probability of H given E divided by the probability of not H given E is equal to the probability of E given H divided by the probability of E given not H times the probability of H divided by the probability of not H. This is called the odds form because it's expressed as odds. Like, odds are always ratios, like 2 to 1, and that's basically like the division that's going on here, right? This is a ratio of one quantity to another. But anyway, here's an explanation of odds from 3 Blue, 1 Brown.
If you've ever heard someone talk about the chances of an event being 1 to 1 or 2 to 1, things like that, you already know about odds. With probability, we're taking the ratio of the number of positive cases out of all possible cases, right? Things like 1 in 5 or 1 in 10. With odds, what you do is take the ratio of all positive cases to all negative cases. You commonly see odds written with a colon to emphasize the distinction, but it's still just a fraction, just a number. So an event with a 50% probability would be described as having 1 to 1 odds. A 10% probability is the same as 1 to 9 odds. An 80% probability is the same as 4 to 1 odds. You get the point. It's the same information. It still describes the chances of a random event, but it's presented a little differently, like a different unit system. Probabilities are constrained between 0 and 1, with even chances sitting at 0.5. But odds range from 0 up to infinity, with even chances sitting at the number 1.
So we can actually put the odds form of Bayes' theorem in slogan form. The slogan is that the posterior odds equals the likelihood ratio times the prior odds. So on the left side here, this left term is called the ratio of the posteriors, or the posterior ratio, or the posterior odds. The middle term is called the likelihood ratio, or the Bayes factor, or the relative likelihoods. And finally, the right term here is called the ratio of the priors, or the prior ratio, or the prior odds. Any of these terms are adequate. Now you might be wondering, how does the odds form of Bayes' theorem relate to the standard form of Bayes' theorem? Well, the odds form is actually a straightforward consequence of the standard form of Bayes' theorem. So we have the odds form up here, and look, we have the standard form of Bayes' theorem right here. The probability of H given E is equal to the probability of E given H times the probability of H divided by the probability of E. We also have another instance of the standard form of Bayes' theorem here, but instead of plugging in H, we've just plugged in not H as our hypothesis. But these are both just instances of the standard form of Bayes' theorem. All you have to do is just divide the probability of H given E by the probability of not H given E, and that'll give you the left-hand side of this equation up here, the odds form. And when you do that, since this is identical to this, and this is identical to this, when you divide this by this, it just equals this divided by this. And of course, when you divide these two right-hand sides, the P of E in the denominator of both crosses out. That's how division works with fractions. And when you cross off P of E, you get the odds form of Bayes' theorem. So the odds form is a straightforward consequence of the standard form of Bayes' theorem. Here, then, is a handy-dandy example of the odds form of Bayes' theorem in action. I don't know why it's telling me that I spelled diseaseitis wrong. That's totally a legitimate disease. I got it last week. it means inflammation of the disease. It's real. Fox News told me so. So suppose you are a nurse screening patients for diseaseitis. The screening test involves a tongue depressor that usually turns black for patients who have the sickness. Suppose you know the following. 20% of the patients in the screening population actually have diseaseitis. Among the patients with diseaseitis, 90% of them turn the tongue depressor black. Those are the true positives. However, 15% of the patients without diseaseitis will also turn the tongue depressor black. Those are the false positives. The question now is, what is the probability that a patient with a blackened tongue depressor actually has diseaseitis? So to answer this, we can use the odds form of Bayes' theorem. Just let H be the hypothesis that the patient has diseaseitis, and so then not H, or the negation of H, is going to be that the patient does not have diseaseitis. And then we're going to let E, or our data or our evidence, be the evidence of a blackened tongue depressor. With this in hand, let's reason this out. So because 20% of the population has diseaseitis, while 80% of the population doesn't, the ratio of the priors, that is the ratio of the probability of H to the probability of not H, is 1 to 4, right? Because the probability of H is going to be 20%, the probability of not H is 80%, and the ratio of 20 to 80 is just a 1 to 4 ratio. Another way to think about that is that we're starting off with 4 times fewer people with diseaseitis as people without it. So we've got the ratio of the priors. Then each person with the disease is 90% likely to make the depressor black. And each person without the disease is only 15% likely to make the depressor black. So we're saying that the probability that someone makes the depressor black, given that they have the disease, so given H, is 90%. While the probability that they make the depressor black, given that they don't have the disease, is only 15%. So these are our likelihoods, right? This is the likelihood of H, and this is the likelihood of not H. Again, keep in mind from earlier on in the video that that's unfortunately named because likelihood sounds like probability. Again, think of the likelihood of H as just the probability of the evidence given that H is true. And the likelihood of not H is the probability that the evidence would be true given the truth of not H. So what then is the likelihood ratio? Well, all you got to do is 90% to 15%, right? The likelihood ratio is 90% up here to 15% down here. 90 to 15. That is 6 to 1, right? Right, 90 divided by 15 is 6. So the likelihood ratio is 6 to 1. Again, another way to think about this is that each person with diseaseitis is 6 times as likely as a person without diseaseitis to make the tongue depressor black. So then how do we determine the posterior odds? Well, all you got to do, right? Remember our slogan, the posterior odds equals the likelihood ratio times the prior odds. So all you got to do is the likelihood ratio, 6 over 1, times the prior odds, 1 over 4, gives us the posterior odds, 6 over 4. And of course, you can simplify that to give us 3 to 2. So what that tells us is that the ratio of the posteriors is 3 to 2. The ratio between the probability of H given E and the probability of not H given E is 3 to 2. To convert this relative proportion into an absolute probability that a random person who blackened the tongue depressor really does have diseaseitis, we do 3 divided by 3 plus 2 to see that 3/5, or 60% of those who blacken the tongue depressor really do have diseaseitis. In other words, given that a random person did in fact blacken the tongue depressor, the probability that they have diseaseitis is 60%. So that gives us the probability of H given E. And that's what we wanted to determine. Now, you might not immediately see why, in order to convert this to an absolute probability, we do 3 divided by 3 plus 2. Think about it like this. When you have mutually incompatible but exhaustive hypotheses, and the ratio of one to another in the probability space is like x to y, well then to determine the absolute probability of the former, we're just going to do x divided by x plus y. So let's take an example. I made that a little bit too abstract. Suppose we have a kindergarten class, and in the kindergarten class, of course, there are males and females. Ignore intersex conditions. Okay, I know some of you are like, well, actually. So within this class, we've just got males or females. No one is both a male or a female, and no one is neither a male nor female. Now suppose that I told you that the ratio of males to females in this class is 3 to 2. So for every 3 males, there are 2 females in this class. Now suppose I ask you, like, what's the absolute probability that a random child chosen from this class is going to be a male? Well, I mean, just think about that intuitively. If the ratio of males to females is 3 to 2, well, then what that means is that 3 out of every 5 students is going to be a male, right? Because it's 3 males, 2 females. So 3 out of 3 plus 2, right? It's the males out of the males plus the females. So it's 3 out of 3 plus 2, or 3/5, or 60%. So I hope that gives you a kind of intuitive sense of why we do this calculation here. And notice that we can now see why the answer to the original problem posed at the beginning of my video is D. Remember, only 1% of women her age have cancer, and the test was 90% accurate. So when we let cancer be H, no cancer be not H, and E be the evidence of a positive test result, if we want to determine the probability that she has cancer given that she has a positive test result, we can use the odds form of Bayes' theorem. In particular, we want to find the posterior ratio by multiplying the likelihood ratio by the prior ratio. So what's the ratio of the priors? Well, the ratio of the priors is 1 to 99, right? Because 1% of women her age have cancer, so the probability that she has it before looking at this evidence is 1%. And of course, what that means is that there's a 99% chance that she doesn't have it. And so the prior ratio is 1% to 99%, or 1 to 99. And then we can ask, what is the likelihood ratio? Well, in order to determine that, we need to know the numerator here and the denominator here. The numerator here is the probability that she has a positive test result given that she has cancer. Well, remember, the test is 90% accurate. So given that she really does have cancer, there's a 90% chance that the test will indicate that she has cancer, and that is give a positive test result. So the probability of E given H is 90%. By contrast, the probability of E given not H is 10%, right? Because conditional on her not having cancer, there's still a 10% chance that the test would go wrong. That is, that the test would give a positive test result, positive for cancer. So the probability of E given not H is 10%. And what that means is that the likelihood ratio is 9 to 1, right? Because the numerator here is 90%, the denominator here is 10%, and 90% to 10%, right? That's a ratio of 9 to 1. So then we multiply the likelihood ratio by the ratio of the priors in order to get 9 to 99, or simplifying, 1 to 11. Again, keep in mind that this is the ratio of the posteriors. 1 to 11, or 1 divided by 11, that is not the probability that she has cancer given that she tested positive. This is the ratio between the probability that she has cancer given that she tested positive, on the one hand, and on the other hand, the probability that she doesn't have cancer given that she tested positive. Okay, so this is just a ratio of these two posterior probabilities. Again, if you want to convert that to an absolute probability, the absolute probability that she has cancer given that she tested positive, we do 1 divided by 1 plus 11, right? That was the 3 divided by 3 plus 2 in the last example. And in this case, we just do 1 divided by 1 plus 11, which is 1/12, or in other words, 8%. So 8% is the probability that she has cancer given that she tested positive. So she doesn't have too much to worry about. It's literally 92% probable that she doesn't have cancer in light of this evidence. And of course, given that it's 8%, we know that D is the correct answer. And then here's a final note about the odds form of Bayes' theorem. Importantly, it isn't absolutely necessary to use H and not H as our hypotheses, right? H and then the strict logical negation of H. We can instead use competing hypotheses that are not strict negations of one another. For example, we could use like theism and naturalism as our hypotheses, even though naturalism isn't the strict negation of theism and theism isn't the strict negation of naturalism. Of course, they can't both be true, right? So they're incompatible, but they could, in principle, both be false. So they don't exhaust the space of possibilities, and they also don't exhaust the probability space. Just note, and this is a very important note, when you use the odds form of Bayes' theorem, and when you don't have a hypothesis and the strict negation of that hypothesis, and so when you don't have mutually exhaustive alternatives, this last step will not go through, okay? Do not use this last step when that condition is met, right? All you're going to be able to conclude when you use, for instance, theism and naturalism is the ratio of the posteriors. That is, the ratio between, say, the probability of theism given some evidence and the probability of naturalism given some evidence. You won't then be able to convert that to an absolute probability in the way described on the screen here. And again, the reason is because like naturalism and theism don't exhaust the possibility or the probability space. And so, for instance, like a 1-to-1 posterior ratio between them might, in principle, correspond to, for example, theism and naturalism each having only an absolute probability of, let's say, 25%, given the evidence in question. Right, so both of them might be 25%, and the ratio of 25% to 25% is 1-to-1, right? And yet, if you use this method down here, you would get 1 divided by 1 plus 1, 1 divided by 2, which is 50%, right? So just be careful when you're converting to absolute probabilities. You're going to want to make sure that you have mutually exclusive and exhaustive hypotheses up here. All right, now we're on to evidence. Show me the evidence. Show me the evidence.
Show me the evidence. Show me the evidence.
Okay, Bayesians generally conceive of evidential support as probability raising. In other words, some piece of evidence or data E evidentially supports or confirms a hypothesis H, just in case E raises the probability of H. More precisely, E is evidence for H, or E would be evidence for H, just in case the probability of H given E is greater than the probability of H. You can see here that E is raising or boosting or increasing the probability of H. And this, by the way, is often known as the positive relevance account of evidence. And it's plausible too, right? Think about this biconditional. This is saying E is evident for H if and only if this condition is met. So let's do the left to right-hand side of the biconditional. If E is evidence for H, well then E is going to raise the probability of H. Yeah, that's plausible, right? If something is evidence for a hypothesis, surely it's then going to raise the probability of the hypothesis. It's going to make the hypothesis more likely than it would be otherwise. Evidence counts in favor of a hypothesis. It supports it. It has to raise its probability. And similarly, you might think that the right to left direction is also plausible. If some piece of data really does raise the probability of a hypothesis, well, then surely it's evidence for the hypothesis. It's counting in its favor. It's supporting it. It's giving it a probabilistic boost. So the biconditional, you might think, is plausible. How, though, does this relate to Bayes' theorem, you ask? Well, it's pretty straightforward to see that this condition holds, this condition holds just in case the likelihood ratio is greater than 1. That is, just in case the probability of E given H is greater than the probability of E given not H. To put it differently, E is evidence for H, just in case E is more expected under H than it is under the negation of H. So when E is more expected on a hypothesis, or less surprising on a hypothesis, or more probable on that hypothesis than the evidence is on the negation of that hypothesis, then and only then does that piece of data count as evidence for the hypothesis. This is why you'll often hear people saying, hey, this piece of data is more expected on theism than it is under naturalism, and so it counts as evidence for theism. Or you'll hear people say that, hey, this data is less surprising on naturalism, that is, it's more expected under naturalism, it's more probable under naturalism than it is under theism, and hence it's evidence for naturalism over and against theism. So yeah, E is evidence for H just in case E raises the probability of H. That is, the probability of H given E is greater than the probability of H. And that happens just in case the likelihood ratio is greater than 1. More technically, it's when the likelihood ratio is greater than 1 when you have H in the numerator here. If you switched up these two and you put not H in the numerator, well then E would be evidence for H when this likelihood ratio is less than 1, because then the probability of H given E is going to be in the denominator, and so you're basically flipping all these. And so then if E is more expected under H than it is under not H, well then the likelihood ratio would actually be bottom heavy. And so the bottom number would be greater than the top number, in which case the likelihood ratio as a whole would be less than 1. But yet E would still be evidence for H. Okay, anyway, that's a technical aside. You get my point, right? When you have H's on the top and not H on the bottom, well then E is evidence for H, just in case the likelihood ratio is greater than 1. And just think of that in terms of E being more expected under H than it is under not H, or E being more likely under H, or E being more probable under H than it is under not H. So anyway, to see why this is true, to see why the probability of H given E is greater than the probability of H, just in case the likelihood ratio is greater than 1, we're going to have to recall the odds form of Bayes' theorem. The posterior ratio is equal to the likelihood ratio times the prior ratio. Suppose we have some fixed value for the probability of H, okay? And we're going to call that fixed value K. So I'm just plugging in K here. And of course, when the probability of H is K, well, then the probability of not H is just 1 minus K, right? If the probability of H is 0.7, well, then the probability that H is false, that is the probability of not H, is going to be 1 minus 0.7, or 0.3. So if we have a fixed value for the probability of H, if we fix that at K, well, then the prior ratio is going to be the fixed value of K over 1 minus K. So now we're going to let the likelihood ratio be exactly 1. So then we have 1 times K over 1 minus K, and of course, 1 times something is just that thing, right? So we get the posterior ratio is equal to K divided by 1 minus K. But then the posterior ratio is just the same thing as the prior ratio, right? And again, if you want to turn the probability of H given E into an absolute probability here, what you do is K divided by K plus 1 minus K, right? So in order to convert this ratio, or this relative proportion, into an absolute proportion, or an absolute probability, you do the numerator divided by the numerator plus the denominator. So you do K divided by K plus 1 minus K. And of course, k divided by k plus 1 minus k is just k divided by 1, and that's just k, right? And so the absolute value of the probability of h given e is equal to k. But remember, we supposed that the probability of h was just k, and so we just concluded that the probability of h given e is equal to the probability of h, and that's just equal to k. So when the likelihood ratio is 1, right, that was our supposition, we suppose that the likelihood ratio is 1, it follows that e isn't evidence for h. Right, look, because e didn't raise the probability of h. The probability of h conditional on e just is the same thing as the probability of h, so e didn't raise its probability. This condition up here isn't met. And so when the likelihood ratio is 1, e is not evidence for h. But now suppose that the likelihood ratio here is greater than 1. Say it's 2. 2 is just an arbitrary number. My point would apply to any number greater than 1, but we're just going to pick one for ease. Okay, so we're going to pick the number 2. So we're going to suppose that the likelihood ratio is greater than 1. We're going to say that it's 2. And that, of course, is going to give us 2 times k over 1 minus k, right? Remember, we're still keeping the assumption that the probability of h is k, and so the ratio of the priors is still k to 1 minus k. But this time, instead of multiplying by 1, we're multiplying by 2, because the likelihood ratio is greater than 1. We're supposing that it's 2. And this, in turn, gives us that the posterior ratio is equal to 2k divided by 1 minus k. Notice what we've done here. We have the posterior ratio here. We have the posterior ratio here. This is from the previous case that we looked at when the likelihood ratio is 1. This is the current case when the likelihood ratio is 2. Notice what we've done here. We've increased the numerator by a factor of 2, going from this case to this case, while keeping the denominator exactly the same. We've therefore doubled the odds of the probability of h given e in relation to the probability of not h given e. If the odds were, say, 1 to 1 when the likelihood ratio is 1, the odds when the likelihood ratio is 2 become 2 to 1. If the odds were, say, 1 to 100 when the likelihood ratio is 1, they're now 2 to 100 when the likelihood ratio is 2. This in turn means that when we shift from a likelihood ratio of 1 to a likelihood ratio of 2, the posterior odds become more favorable to the probability of h given e, right? They become more top-heavy. And hence the probability of h given e is higher when the likelihood ratio is 2 compared to when the likelihood ratio is 1, right? Because the posterior odds going from the former case to the present case have become more favorable to the probability of h given e. The posterior odds have in fact doubled in its favor. And this point, of course, easily generalizes to any likelihood ratio greater than 1. If the likelihood ratio were 3, well then when we compare this case to this case, we would have tripled the odds in favor of the probability of h given e in relation to the probability of not h given e. So this point, again, easily generalizes to any likelihood ratio greater than 1. But we've already seen that when the likelihood ratio is 1, right, the probability of h given e is equal to k, right? That's what we showed last time. When the likelihood ratio is equal to 1, the posterior probability of h, that is the probability of h given e, just equals the prior probability of h, which equals k. That's what happens when the likelihood ratio is 1. But we just concluded that when the likelihood ratio is greater than 1, right, we increase the odds in favor of the probability of h given e. And as a result of that, the posterior probability of h, that is the probability of h given e, has increased. And hence, the probability of h given e has to be greater than k, right? If the probability of h given e was k in this case, and then going from here to here, we've increased the probability of h given e, well then the probability of h given e in this case has got to be greater than k. And hence, in this case, the probability of h given e is greater than the probability of h. And what that means is that e has raised the probability of h. E is evidence for h. That's what happens when the likelihood ratio is greater than 1. When the likelihood ratio is greater than 1, e is evidence for h. And similar reasoning shows that the probability of h given e is less than the probability of h when the likelihood ratio is less than 1. Instead of increasing the odds in favor of the numerator here, you'll be decreasing the odds against the numerator here. And the effect of that on the absolute probability of the numerator here will be to diminish it. The result of this is that the likelihood ratio is the key to evidential confirmation or disconfirmation. When the likelihood ratio is greater than 1, the probability of h given e is greater than the probability of h, and hence e is evidence for h. In such a case, e confirms h, or supports h, or raises the probability of h. By contrast, when the likelihood ratio is less than 1, the probability of h given e is less than the probability of h, and hence e is evidence against h. E disconfirms h, or lowers the probability of h. Equivalently, in this case, e is going to be evidence for the negation of h. E is going to confirm the negation of h, or raise the probability of the negation of h. And finally, when the likelihood ratio is 1, the probability of H given E is equal to the probability of H, and hence E is evidentially irrelevant to H. It neither confirms nor disconfirms H. It neither increases nor decreases the probability of H. So here then are some important Bayesian facts. In the preceding reasoning, I actually only showed the left to right-hand side of these biconditionals, but it's very straightforward to show the right to left direction in basically the same way that I just did. So E is evidence for H if and only if the likelihood ratio of H to not H is greater than 1. In other words, E is evidence for H if and only if E is more expected or more probable or more likely on H than not H. In other words, E is less surprising on H than it is on not H. E is evidence against H if and only if the likelihood ratio is less than 1. E is less expected or less probable or less likely on H than not H. In other words, E is more expected on the negation of the hypothesis than it is under the hypothesis itself. Finally, E is irrelevant to H if and only if the likelihood ratio is equal to 1. E is then equally expected or equally probable or equally likely on both H and not H. And once again, this is why you hear people in philosophy say things like, this data is more expected under one hypothesis than under the other, and hence it counts as evidence for the former over the latter. Notice also how all of this is comparative in nature, right? For some piece of evidence or some piece of data to confirm a hypothesis, that is to be evidence for the hypothesis, the evidence can still actually be quite unlikely on that hypothesis. What matters is that the evidence is even more unlikely on the negation of that hypothesis, right? So some data could still be very surprising on a hypothesis, and yet not count as evidence against that hypothesis, because that evidence might very well be even more surprising under the negation of that hypothesis, or it might be just as surprising. So take that to heart. The probability of some evidence, given a hypothesis, can be very low. The evidence can be very surprising on the hypothesis. It can be not at all what you expect on the hypothesis, and yet it doesn't thereby follow that that data, that evidence is evidence against the hypothesis. Oftentimes it will be, because the negation of that hypothesis will predict the data better, it won't be as surprising, but perhaps not. Perhaps the data is equally unexpected or even more unexpected under the negation of that hypothesis. So keep that in mind. Keep the comparative nature of Bayesian confirmation in mind. I'll cover this later on. I'll talk about it in more detail, but it's important to note here because this is where it's directly relevant. And also think about that intuitively, like it makes sense. Suppose that my roommate and I, we take turns taking out the trash. I do it every Sunday, he does it every Wednesday or something. And suppose we're both really diligent about this. My roommate knows that I know about this. I know that he knows about this. I've been doing this for the past year, let's say, and I haven't missed a single day. So we're both really diligent about this, and we know this about each other. Now suppose I wake up on Sunday to see written on the whiteboard in the corner, "Don't forget to take out the trash." And suppose we have two hypotheses and we're trying to evaluate the probability of these hypotheses in light of this evidence, in light of the fact that this message is written on the whiteboard. One hypothesis says that my roommate did it and he's reminding me. The other hypothesis is just that, like, the marker magically flew up and took off its cap and then wrote that by itself. Now, given my setup, it actually does seem pretty surprising that my roommate would write this on the board. My roommate knows that I know this. Like, I've never failed to bring out the trash. Why would he do this? And I mean, that's my whiteboard. It's my marker. He usually doesn't touch my stuff. So, like, this is really out of character for him. It's really weird. I've been doing this for over a year. Neither of us have ever forgotten. So, like, why would he write that? It seems really surprising. But do you know what's even more surprising? if the marker magically did it itself. And so even though it's very surprising, even though the evidence is very surprising under the hypothesis that my roommate did this, even though it's not at all probable under that hypothesis, the evidence is still far more probable under that hypothesis than it is under this competing hypothesis. And so we still have very powerful evidence for the former over the latter. And so it makes sense that something can still be evidence for one hypothesis over another, even though the evidence is unlikely or unexpected or surprising on the former. Finally, another way to think of evidential support that's ultimately equivalent but differs in emphasis from the ways that we've been looking at it so far takes its cue from the standard form of Bayes' theorem. So recall the standard form, which is right here. The probability of H given E is equal to the probability of E given H times the probability of H divided by the probability of E. Now you can think of this standard form as basically the probability of H given E is equal to the probability of H times this factor here. This is not the Bayes factor. The Bayes factor is just the likelihood ratio, okay? So I actually don't know what this factor is called here. Let's call it the Joe factor. Okay, so think of the standard form of Bayes' theorem as the posterior probability of H, or the probability of H given E, is equal to the Joe factor times the probability of H. Now we can ask, under what condition is the probability of H given E greater than the probability of H? That is, under what condition does E raise the probability of H? Under what condition is E evidence for H? Well, examining the equation here, that happens just in case the probability of E given H is greater than the probability of E, right? Just in case the Joe factor is greater than 1, right? If the Joe factor is greater than 1, well then when you multiply something greater than 1 by the probability of H, this thing on the left here has to be greater than the probability of H, right? So when the Joe factor is greater than 1, that is, when the numerator is greater than the denominator, we have the posterior probability of H being greater than the prior probability of H. And so what that means is that E is evidence for H, that is, E raises the probability of H when H renders E more probable than E would have been otherwise, right? This is H rendering E more probable than E would have been otherwise. And when that happens, E is evidence for H. So this is another way to think about evidence. Usually, though, it's much easier to calculate the likelihood ratio and to use that as a guide to evidential support. But I did just want to put this on your radar because it's important. All right, so we've gone through Bayes' theorem, we've gone through evidence, we've gone through probability, we've gone through all this stuff, but you may still find yourself without a kind of intuitive grasp of Bayes' theorem, and that's where I think visualizations can really help. They can transform your thinking and help you see the power, the truth, the utility, and the ultimate why behind Bayes' theorem. And so to that end, we are going to be watching 3 videos. They're not super duper long. The first one is from 3 Blue, 1 Brown, and I'll talk about the second 2 later.
The goal is for you to come away from this video understanding one of the most important formulas in all of probability, Bayes' theorem. This formula, it's central to scientific discovery. It's a core tool in machine learning and AI, and it's even been used for treasure hunting, when in the 1980s, a small team led by Tommy Thompson, and I'm not making up that name, used Bayesian search tactics to help uncover a ship that had sunk a century and a half earlier, and the ship was carrying what, in today's terms, amounts to $700 million worth of gold. So it's a formula worth understanding, but of course, there are multiple different levels of possible understanding. At the simplest, there's just knowing what each one of the parts means, so that you can plug in numbers. Then there's understanding why it's true, and later I'm going to show you a certain diagram that's helpful for rediscovering this formula on the fly as needed. But maybe the most important level is being able to recognize when you need to use it. And with the goal of gaining a deeper understanding, you and I are going to tackle these in reverse order. So before dissecting the formula or explaining the visual that makes it obvious, I'd like to tell you about a man named Steve. Listen carefully now. Steve is very shy and withdrawn, invariably helpful, but with very little interest in people or the world of reality. A meek and tidy soul, he has a need for order and structure, and a passion for detail. Which of the following do you find more likely? Steve is a librarian, or Steve is a farmer? Some of you may recognize this as an example from a study conducted by the 2 psychologists Daniel Kahneman and Amos Tversky. Their work was a big deal. It won a Nobel Prize, and it's been popularized many times over in books like Kahneman's Thinking Fast and Slow or Michael Lewis's The Undoing Project. What they researched was human judgments, with a frequent focus on when these judgments irrationally contradict what the laws of probability suggest they should be. The example with Steve, our maybe librarian, maybe farmer, illustrates one specific type of irrationality. Or maybe I should say alleged irrationality. There are people who debate the conclusion here, but more on all of that later on. According to Kahneman and Tversky, after people are given this description of Steve as a meek and tidy soul, most say that he's more likely to be a librarian. After all, these traits line up better with the stereotypical view of a librarian than a farmer. And according to Kahneman and Tversky, this is irrational. The point is not whether people hold correct or biased views about the personalities of librarians and farmers. It's that almost nobody thinks to incorporate information about the ratio of farmers to librarians in their judgments.
With the tools that we've covered so far, I hope you guys are seeing what's going on. We're given certain data, certain evidence, and we think about how expected that is under the 2 hypotheses. One of the hypotheses is that Steve is a librarian. The other hypothesis is that he's a farmer. And when people are thinking, okay, overall, in light of this evidence, what's the probability that Steve is a librarian? Or what's the probability that he is a farmer? Those are the posterior probabilities. And we know that the ratio of the posteriors is not just a function of the likelihood ratio. That is, it's not just a function of how expected that data is under the hypotheses. Steve fitting that description might be more expected under the hypothesis that he's a librarian than it is under the hypothesis that he is a farmer. But do you know what else you have to keep in mind? Remember the odds form of Bayes' theorem. You have to also keep in mind the ratio of the priors. You can't forget how many farmers there are in relation to librarians. If farmers vastly outnumber librarians in the population, you have to take that into account when you're trying to determine the posterior probabilities. And ignoring the priors in this kind of way is often called base rate neglect. You're ignoring the base rate of librarians in the population, or you're the base rate of farmers in the population. Anyway, I'm kind of anticipating things here, but I did just want to say that and connect it to what we've covered so far.
In their paper, Kahneman and Tversky said that in the US, that ratio is about 20 to 1. The numbers that I could find today put that actually much higher, but let's stick with the 20 to 1 number, since it's a little easier to illustrate and it proves the point just as well. To be clear, anyone who is asked this question is not expected to have perfect information about the actual statistics of farmers and librarians and their personality traits. But the question is whether people even think to consider that ratio, enough to at least make a rough estimate. Rationality is not about knowing facts, it's about recognizing which facts are relevant. Now, if you do think to make that estimate, there's a pretty simple way to reason about the question, which, spoiler alert, involves all of the essential reasoning behind Bayes' theorem. You might start by picturing a representative sample of farmers and librarians, say 200 farmers and 10 librarians. Then, when you hear of this meek and tidy soul description, let's say that your gut instinct is that 40% of librarians would fit that description, and that 10% of farmers would. If those are your estimates, it would mean that from your sample, you would expect about 4 librarians to fit the description, and about 20 farmers to fit that description. So, the probability that a random person among those who fit this description is a librarian is 4 out of 24, or 16.7%. So even if you think that a librarian is 4 times as likely as a farmer to fit this description, that's not enough to overcome the fact that there are way more farmers. The upshot, and this is the key mantra underlying Bayes' theorem, is that new evidence does not completely determine your beliefs in a vacuum. It should update prior beliefs. If this line of reasoning makes sense to you, the way that seeing evidence restricts the space of possibilities, and the ratio you need to consider after that, then congratulations! You understand the heart of Bayes' theorem. Maybe the numbers that you would estimate would be a little bit different, but what matters is how you fit the numbers together to update your beliefs based on evidence. Now, understanding one example is one thing, but see if you can take a minute to generalize everything that we just did and write it all down as a formula.
We're not going to go through this here because we've kind of already cheated. We've gone through the different formulations of Bayes' theorem, so we've already seen the formula. So we're just going to continue on with the video here. I kind of already spoiled it for you. Apologies.
The general situation where Bayes' theorem is relevant is when you have some hypothesis, like Steve is a librarian, and you see some new evidence, say this verbal description of Steve as a meek and tidy soul. And you want to know the probability that your hypothesis holds given that the evidence is true. In the standard notation, this vertical bar means given that, as in we're restricting our view only to the possibilities where the evidence holds. Now remember the first relevant number we used. It was the probability that the hypothesis holds before considering any of that new evidence. In our example, that was 1 out of 21, and it came from considering the ratio of librarians to farmers in the general population. This number is known as the prior. After that, we need to consider the proportion of librarians that fit this description, the probability that we would see the evidence given that the hypothesis is true. Again, when you see this vertical bar, it means we're talking about some proportion of a limited part of the total space of possibilities. In this case, that limited part is the left side, where the hypothesis holds. In the context of Bayes' theorem, this value also has a special name. It's called the likelihood. Similarly, you need to know how much of the other side of the space includes the evidence, the probability of seeing the evidence given that the hypothesis isn't true. This funny little elbow symbol is commonly used in probability to mean not. So with the notation in place, remember what our final answer was. The probability that our librarian hypothesis is true, given the evidence, is the total number of librarians fitting the evidence, 4, divided by the total number of people fitting the evidence, 24. But where did that 4 come from? Well, it's the total number of people times the prior probability of being a librarian, giving us the 10 total librarians, times the probability that one of those fits the evidence. That same number shows up again in the denominator, but we need to add in the rest. The total number of people times the proportion who are not librarians times the proportion of those who fit the evidence, which in our example gives 20. Now notice the total number of people here, 210, that gets cancelled out. And of course it should, that was just an arbitrary choice made for the sake of illustration. This leaves us, finally, with a more abstract representation purely in terms of probabilities. And this, my friends, is Bayes' theorem.
More specifically, going back to my characterizations earlier on, that is the standard form of Bayes' theorem, and remember we actually looked at two different variants of the standard form. One of them only had the probability of E down here in the denominator, but I also explained how that is equivalent to having this longer denominator here. So this is just the second variant of the standard form of Bayes' theorem that we already covered.
More often, you see this denominator written simply as P of E, the total probability of seeing the evidence, which in our example would be the 24 out of 210. But in practice, to calculate it, you almost always have to break it down into the case where the hypothesis is true and the one where it isn't. Capping things off with one final bit of jargon, this answer is called the posterior. It's your belief about the hypothesis after seeing the evidence. Writing it out abstractly might seem more complicated than just thinking through the example directly with a representative sample. And yeah, it is. Keep in mind, though, the value of a formula like this is that it lets you quantify and systematize the idea of changing beliefs. Scientists use this formula when they're analyzing the extent to which new data validates or invalidates their models. Programmers will sometimes use it in building artificial intelligence, where at times you want to explicitly and numerically model a machine's belief. And honestly, just for the way that you view yourself and your own opinions and what it takes for your mind to change, Bayes' theorem has a way of reframing how you even think about thought itself. Putting a formula to it can also be more important as the examples get more and more intricate. However you end up writing it, I actually encourage you not to try memorizing the formula, but to instead draw out this diagram as needed. It's sort of a distilled version of thinking with the representative sample, where we think with areas instead of counts, which is more flexible and easier to sketch on the fly. Rather than bringing to mind some specific number of examples, like 210, think of the space of all possibilities as a 1x1 square. Then, any event occupies some subset of this space, and the probability of that event can be thought about as the area of that subset. So for example, I like to think of the hypothesis as living in the left part of the square with a width of P of H. Now I recognize I'm being a bit repetitive, but when you see evidence, the space of possibilities gets restricted, right? And the crucial part is that that restriction might not be even between the left and the right. So the new probability for the hypothesis is the proportion that it occupies in this restricted wonky shape. Now, if you happen to think that a farmer is just as likely to fit the evidence as a librarian, then the proportion doesn't change, which should make sense, right? Irrelevant evidence doesn't change your beliefs. But when these likelihoods are very different from each other, that's when your belief changes a lot. Bayes' theorem spells out what that proportion is, and if you want, you can read it geometrically. Something like P of H times P of E given H, the probability of both the hypothesis and the evidence occurring together, is the width times the height of this little left rectangle, the area of that region. Alright, this is probably a good time to take a step back and consider a few of the broader takeaways about how to make probability more intuitive, beyond just Bayes' theorem. First off, notice how the trick of thinking about a representative sample with some specific number of people, like our 210 librarians and farmers, was really helpful. There's actually another Kahneman and Tversky result which is all about this, and it's interesting enough to interject here. They did this experiment that was similar to the one with Steve, but where people were given the following description of a fictitious woman named Linda. Linda is 31 years old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and also participated in the anti-nuclear demonstrations. After seeing this, people were asked what's more likely? 1, that Linda is a bank teller, or 2, that Linda is a bank teller and is active in the feminist movement. 85% of participants said that the latter is more likely than the former, even though the set of bank tellers who are active in the feminist movement is a subset of the set of bank tellers. It has to be smaller. So that's interesting enough. But what's fascinating is that there's a simple way that you can rephrase the question that dropped this error from 85% to 0. Instead, if participants were told that there are 100 people who fit this description, and then they're asked to estimate how many of those 100 are bank tellers, and how many of them are bank tellers who are active in the feminist movement, nobody makes the error. Everybody correctly assigns a higher number to the first option than to the second. It's weird. Somehow phrases like 40 out of 100 kick our intuitions into gear much more effectively than 40%, much less 0.4, and much less abstractly referencing the idea of something being more or less likely. That said, representative samples don't easily capture the continuous nature of probability, so turning to area is a nice alternative, not just because of the continuity, but also because it's way easier to sketch out when you're sitting there pencil and paper puzzling over some problem. You see, people often think about probability as being the study of uncertainty, and that is of course how it's applied in science, but the actual math of probability, where all the formulas come from, is just the math of proportions. And in that context, turning to geometry is exceedingly helpful. I mean, take a look at Bayes' theorem as a statement about proportions, whether that's proportions of people, of areas, whatever. Once you digest what it's saying, it's actually kind of obvious. Both sides tell you to look at the cases where the evidence is true, and then to consider the proportion of those cases where the hypothesis is also true. That's it. That's all it's saying. The right-hand side just spells out how to compute it. What's noteworthy is that such a straightforward fact about proportions can become hugely significant for science, for artificial intelligence, and really any situation where you want to quantify belief. As I mentioned, some psychologists debate Kahneman and Tversky's conclusion that the rational thing to do is to bring to mind the ratio of farmers to librarians. They complain that the context is ambiguous. I mean, who is Steve, exactly? Should you expect that he's a randomly sampled American? Or would you be better to assume that he's a friend of the two psychologists interrogating you? Or maybe that he's someone that you're personally likely to know? This assumption determines the prior. I, for one, run into way more librarians in a given month than I do farmers. And needless to say, the probability of a librarian or a farmer fitting this description is highly open to interpretation. For our purposes, understanding the math, what I want to emphasize is that any question worth debating here can be pictured in the context of the diagram. Questions about the context shift around the prior, and questions about the personalities and stereotypes shift around the relevant likelihoods. All that said, whether or not you buy this particular experiment, the ultimate point that evidence should not determine beliefs, but update them, is worth tattooing in your brain. I am in no position to say whether this does or does not run against natural human instinct. We'll leave that to the psychologists. What's more interesting to me is how we can reprogram our intuition to authentically reflect the implications of math, and bringing to mind the right image can often do just that.
And that, of course, is why we're looking at these different visualizations of Bayes' theorem. Okay, so that's the first one by 3 Blue 1 Brown. Next up on the list are 2 videos produced by philosopher Ben Page. These videos are actually based on a paper that he has on academia.edu. I'll put a link to this in the description. And what he's using is a Bayesian bar. So this is basically, I'm terrible. This is basically the exact same thing as the square that we just saw in the 3 Blue 1 Brown video, but instead of a square, you're just using a bar, a rectangle. Still though, Ben Page uses this in the context of philosophy and gives some philosophical examples, so I think it's really important to go through it. And also, it just allows you a panoply of different ways to represent Bayes' theorem and probabilistic reasoning. If you like the bar, you can go with that. If you like the boxes, you can go with that. What matters is that we have a visual way of accurately depicting how we should reason probabilistically.
If you're anything like me, you'll have the experience of reading a philosophy essay, one you enjoy, one you actually understand, but then all of a sudden, a section appears with a load of mathematical formulae. You've reached the Bayesian probability section, and your eyes glaze over, and you think, oh, I dropped maths for a reason. Well, in this video, I want to talk about how we can do Bayesian probability visually using a method that I learned from John Hawthorne. Before I let you in on the secret as to how to think about Bayesian probability visually, I've got 4 preliminaries to run through. The first is that the argument I will use, which is the problem of evil, is meant as an illustration only, and so I won't be going into it in any detail here. The second is that I won't really spend any time justifying the numbers or probability assignments that I give in the argument, as that would take us into the details of it. These are somewhat arbitrary values that I use for the sake of illustration, so try not to get too hung up on whether you think they are accurate. Third, I'm not going to discuss different interpretations of probability, such as frequency, propensity, and degrees of belief interpretations. And finally, we're going to think that something is evidence for a theory if it raises the probability of that theory being true, and something is evidence against a theory if it lowers the probability of that theory being true. Now, if you want to learn more about these preliminaries, then I will be doing some future videos in probability visually. Remember to subscribe. So in order to think about Bayesian probability visually, we're going to introduce something called the Bayesian bar, after the Reverend Thomas Bayes, who came up with Bayes' theorem. And the Bayesian bar is just a rectangle. What's important about the rectangle is its surface area, as this is our total probability space and has the value 1. This is because it contains all our different probabilities, and we're certain that at least one of them is going to be true. We can now split the bar up into further probabilities. So let's imagine someone who is what we'll call a perfect agnostic about God's existence, since they're 50-50 as to whether God exists. So for this perfect agnostic, we can designate half the bar to represent how likely they think it is that God exists, which we'll call theism, and the other half to how likely they think it is that God doesn't exist, which we'll call atheism. Now imagine our agnostic has never considered any evidence for theism or atheism. There are a number of different types of evidences that he could consider, but suppose he starts by thinking how likely or not the existence of God would be if there's evil in the world. Imagine he starts with the theistic half of the bar and asks himself, suppose God exists, how likely would it be that there is evil in the world? Maybe he thinks that because God is all-powerful, all-knowing, and wholly good, the existence of evil doesn't seem very likely at all. But perhaps he also thinks it's not impossible that God and evil exist together, and so he gives 3/4 of the theistic portion of the bar to theism and no evil, and 1/4 of it to theism and evil.
Importantly, keep in mind that this is 3/4 of the theistic bar, right? We're not saying that this is 3/4 probable, like all things considered, right? Remember, the total probability space is the bar as a whole, right? So when we say 3/4, notice that he said 3/4 of the theistic bar.
And 1/4 of it to theism and evil. Now he starts to think about the atheist portion of the bar and thinks, suppose God doesn't exist, how likely is it that there would be evil? This time he thinks it's pretty likely that there would be evil if there's no God, because there's no being like God trying to prevent it, and he thinks it would be pretty unlikely that there would be no evil in an atheist world. So he gives 3/4 of the atheistic portion to atheism and evil, and 1/4 to atheism and no evil. The next step is to think about these different probabilities in terms of the whole bar, rather than just the theistic and atheistic portions. So the probability of theism and no evil in terms of the whole bar is 3/8. Of theism and evil is 1/8. Of atheism and evil is also 3/8. And of atheism and no evil is also 1/8.
And of course, just to cross our T's and dot our I's, that's because this was originally 3/4 of the theistic bar. The theistic bar was 1/2 of the total bar. So 3/4 times 1/2 is going to be 3/8. And you do similar calculations for the rest of them.
And if we add up all these individual probabilities, we get the value 1. Suppose now our agnostic comes across some evil for the first time. This gives him some evidence, namely that evil exists, and as a result the bar is going to change. What he now needs to do is remove 2 portions of the bar where it says there is no evil, since he has found out that there is evil. So both the theism and no evil and atheism and no evil sections must go. Because of this, he has a bar which is smaller than the one before, but the probabilities of this bar must also add up to 1, since it now contains the whole probability space, and at present, they don't add up to 1. So he's going to have to perform a process called renormalization. This sounds more complicated than it is, And it's just the process of changing the values of the remaining probability segments whilst preserving their ratios. So this means that because the atheism and evil section is currently 3 times the size of the theism and evil section, it must also be 3 times the size after this process. So the probability of theism and evil changes from 1/8 to 1/4, and the probability of atheism and evil changes from 3/8 to 3/4. So this gives our perfect agnostic his final probabilities.
And just to give you a way to calculate that, remember this was 3/8 and this was 1/8. Now what you want to do if you want to renormalize that is to find the ratio between the surface area of this bar and the surface area of this bar. Remember this one was 3/8 of the whole bar, this one was 1/8 of the whole bar. So the ratio between those is 3/8 divided by 1/8. 3/8 divided by 1/8 is just 3/1. So what that means is the ratio of this surface area of this bar here to this is 3:1. And of course, when you have a ratio of 3:1 and you want to renormalize that so that it takes up the whole of the probability space, you do the same calculation that we did in the case of the males and females in the class of the kindergartners, right? Remember that one was 3:2. So if you wanted to find the absolute proportion of males in the class as a whole, you'd do 3 divided by 3 plus 2, or 3 out of 5, which is 3/5. Similarly, when we have a 3:1 ratio here, if you want to find out the proportion that the surface area of this bar takes up among the whole bar here, you do 3 divided by 3 plus 1, and that's 3/4. And of course, the remaining bit of the bar is going to be 1/4, because again, we're renormalizing. Given that we've learned that there's evil, we're crossing off the spaces in which there's no evil, and so this is our total probability space here. And it's got to add up to 1, so we have 3/4 and 1/4. We've ruled out the cases in which evil doesn't exist, because we know that evil exists. Okay, so anyway, that's basically a step-by-step guide as to how you can renormalize.
Given the existence of evil, he now thinks the existence of God, theism, has the probability of 1/4 or 25%, as only 1/4 of his final bar is taken up by theism. On the other hand, he now thinks that atheism has the probability of 3/4 or 75%. In other words, whilst there might still be a God who has chosen to allow evil, it's more likely that God doesn't exist, given the existence of evil. The overall result is therefore that evil is evidence for atheism. And the reason for this is that evil raised the probability of atheism from 1/2, represented in our initial bar, to 3/4, which is represented in our final bar. And evil decreased the probability of theism from 1/2, again represented in our initial bar, to 1/4, as we can see in our final bar. So before I end this video, let's go through one more example, and this time we're not going to put any values on the bar, so you can see that the Bayesian bar works just visually on its own. So let's again think about the problem of evil, but this time the person we're going to be thinking about is someone who thinks that theism is really likely and atheism is not that likely. So now we're going to have to split up the theistic portion of the bar further, remembering that we're assuming this person is assigning probabilities in a vacuum, so before they have any evidence that evil does or doesn't exist. Again, we're going to think a lot of the theistic portion is going to be for God and no evil, because we think that God wouldn't want there to be evil in the world and would try to prevent it. And then the remaining part of the theistic portion of the bar is going to be for God and evil. And then on the atheist side, maybe this time we're 50-50, as we think that atheism and evil is kind of just as likely as atheism and no evil. So now we add in our evidence that there is evil in the world, and so we remove the portions of our bar where it says there is no evil. So theism and no evil, and atheism and no evil. And so we're just left with a bar that has just theism and evil, and atheism and evil. And you can see our final probabilities just by looking at the bar. So the question now is evil evidence for theism or atheism? The answer to this is going to be atheism again. And that's because atheism is now more probable than it was to begin with, and theism is less probable than it was to begin with. And remember, we're thinking about evidence as probability raising, and so evil raises the probability of atheism. And this is the case even though in our example theism is still more probable overall, since it takes up the biggest portion of our bar. So that's how to think about probability visually. In a future video, I'll talk about how the Bayesian bar relates to Bayes' theorem, and how the actual formula maps onto this visual bar. In a previous video, I explained how to think about probabilistic reasoning visually by using the Bayesian bar. If you haven't already seen that video, I'd recommend that you watch it before continuing with this one, as I'm now going to explain how the Bayesian bar relates to Bayes' theorem. As a result of this, the content in this video is going to get a bit more technical, but by using the bar, you'll see that it is simpler than it initially looks. In order to show you how the Bayesian bar relates to Bayes' theorem, we're going to need an example. For this video, we're going to use the example of fine-tuning arguments for theism, and just as with the previous video, I'm not really going to say anything about this type of argument or justify the probability assignments that I give. All you need to know for our purposes here is that our universe has very finely tuned values that allow for life, and that if these values had been different, then it's very likely that life wouldn't exist. So let's draw a bar of a perfect agnostic who is 50-50 that God exists. So half of the bar is for theism and the other half for atheism. Now, although you could do all of what I'm about to do on one bar, it's easier to show you how it relates to Bayes' theorem if I draw additional bars with extra content on them. So let's now draw another bar just the same as the previous one, but this time we're going to add in how likely we think fine-tuning is on theism and on atheism. Firstly then, theism. We might think fine-tuning is not that surprising on theism, since we think it's likely that God would want a world with living beings in it, perhaps so that he could have a relationship with them, and the goods that come from that. As a result, we give 3/8 of the whole bar to theism and fine-tuning, and 1/8 to theism and no fine-tuning. We then think about the atheist portion of the bar. This time we're going to think that fine-tuning is really unlikely on atheism, as there's no being that wants life, and it seems extraordinarily unlikely that the universe happened to have the life-permitting finely tuned values by chance. So we give 1/8 of the whole bar to atheism and fine-tuning, and 3/8 of the whole bar to atheism and no fine-tuning. We now get some evidence, namely that there's fine-tuning in the world. And so we delete the portions of the bar where it says that there is no fine-tuning. Again, to show this, I'm just going to draw another bar with these sections deleted. Notice also that I've renormalized the probabilistic values of the portions of the bar so that they add up to 1. As I said in the previous video, this is just the process of changing the values of the remaining probability segments whilst preserving their ratios. So because the theism and fine-tuning portion was 3 times the size of the atheism and fine-tuning section, it must be 3 times the size after this process. So the final probability of theism and fine-tuning is 3/4, and the probability of atheism and fine-tuning is 1/4. The overall result then is that fine-tuning is evidence for theism, as it raised the probability of theism and lowered the probability of atheism. Now, before I explain to you how the bar relates to Bayes' theorem, it'll be helpful to introduce you to some jargon. So take a look at the first bar and the half probability assignments we've given to theism and atheism. These are called our prior probabilities, and they're the probabilities we give to set out the degree of certainty we have or ought to have in certain hypotheses before we've taken this bit of evidence into account. How we determine what these values should be is subject to debate, but exploring that will have to wait for another time.
That's where you get into the distinction between subjective and objective Bayesians that we talked about earlier on in this video. Remember, the subjective Bayesians think that so long as you are obeying the 5 core normative rules, you're going to count as rational. But as we saw, that might allow for a lot of subjectivity. And many people think that it's too subjective. So the objective Bayesians put further constraints, and they're going to be focusing largely on constraints imposed on the assignment of prior probabilities. Anyway, that's the debate that he's alluding to. Just wanted to make that connection with earlier on in my video.
Now look at the second bar, and the probability assignments we see there of 1/8, 3/8, 1/8, and 3/8. These are what's called conditional probabilities, since they're in the conditional form. This means that they say, given some x, y has probability of ... So in our example, given theism, fine-tuning has the probability of ... or given atheism, fine-tuning has the probability of ... dot dot dot.
And just a note here, 3/8 is not that conditional probability for theism, right? Given theism, so restricting your focus to the space of theism, 3/4 of that space is occupied by fine-tuning. So the conditional probability under this model here, the conditional probability of fine-tuning given theism is going to be 3/4, not 3/8. I just wanted to clarify that. The 3/8 here is what he wrote, taking into account the proportion of this space here to the total probability space. But the 3/8 is not the conditional probability of fine-tuning given theism. That's going to be 3/4. I just wanted to clarify that.
Now let's look at the final bar and the two probability assignments there. So 3/4 for theism and fine-tuning, and 1/4 for atheism and fine-tuning. These are known as the posterior probabilities. That is the probability after we've taken into account the relevant evidence. With this jargon now explained, let's think about how the bar relates to Bayes' theorem. Bayes' theorem says the probability of the hypothesis given the evidence is equal to the probability of the hypothesis multiplied by the probability of the evidence given the hypothesis divided by the evidence. So here you can see the formula written out in full, with PR standing for probability, H for hypothesis, and E for evidence. The jargon we have just learned is also useful when thinking about the formula, with the probability of the hypothesis given the evidence relating to the posterior probability, the probability of the hypothesis being connected to the prior probability, and the probability of the evidence given the hypothesis linking with the conditional probability. In order to think about how the formula works, let's ask the question, what is the probability of theism given the evidence of fine-tuning? So in this case, H, our hypothesis, is going to stand for theism, and E, our evidence, will be fine-tuning. In order to find out the answer to this, we're going to need to fill in the other half of Bayes' theorem. First of all is the probability of the hypothesis, which in our case is theism. This is going to be a half, and we can see this in our first bar. Next is the probability of the evidence given the hypothesis, which in our case is the probability of fine-tuning given theism. This has the value of 3/4, which we can work out from looking at our second bar. In order to do this, look at the second bar and imagine removing the atheist half of the bar so that all we have left is the theistic half of it. Now ask yourself, how much of the theist part of the bar does fine-tuning take up? The answer is 3/4, and this is the value we put here for the probability of the evidence, fine-tuning, given the hypothesis, theism. So far we've filled in the top part of the Bayesian formula, and now we have to work out what it is that we divide it by, which is the probability of the evidence. To get this value, we have to work out how likely the evidence is, in our case fine-tuning, on any hypothesis, and to do this we need another formula. This one says that we first find out the value of the probability of the evidence given the hypothesis multiplied by the probability of the hypothesis, and then also the value of the probability of the evidence if the hypothesis is false multiplied by the probability of the hypothesis being false. And then we add these two values together. So in our case, we get the probability of fine-tuning given theism, 3/4, which we can work out from looking at our second bar, and multiply it by the probability of theism, which is a half, which we can see in our first bar. We then work out the value of fine-tuning given the falsity of theism. So in our case, the probability of fine-tuning on atheism, as this is the only other hypothesis we're considering. And this has the value of 1/4, which we can work out from looking at our second bar. And then we multiply this by the probability of the falsity of our hypothesis, and so in our case, the probability of atheism. And here we can see that the value is a half, which we can see in our first bar. After getting these values, we add them together. The result of this is a half, and we can check this by looking at our second bar. For if you look at it and add up the two sections of the bar where there is fine-tuning, we can see that it takes up half the space of the whole bar. With that done, we have the three values we need to fill in Bayes' theorem. So a half for the probability of the hypothesis, 3/4 for the probability of the evidence given the hypothesis, and half for the probability of the evidence. So let's answer the question, what's the probability of theism given fine-tuning? First, we input the numbers we have. So it's a half multiplied by 3/4 divided by a half. Since many people find it easier to perform calculations on decimals rather than fractions, that's the same as 0.5 multiplied by 0.75 divided by 0.5. And the answer we get is 0.75 or 3/4. And we can also check that this is right by looking at our third and final bar, where we can see that 3/4 of the bar is for theism and fine-tuning, just as we got here. So that's how the Bayesian bar relates to Bayes' theorem. Whilst this has been a bit more technical, I hope you can see that the formula is easier to fill out when we're using the bar, and the bar is also a helpful way to show you what Bayes' theorem is doing. But remember, as I said to you in the previous video, you can always think about probabilistic arguments in terms of the bar without numbers, if you prefer. But knowing how the formula connects with the bar is helpful, so that you can use the more formal apparatus if you wish, and translate more formal presentations of arguments into the bar.
Alright, so we've gone over different ways to visually represent Bayes' theorem. That was the purpose of this fourth section of my video. If you just follow the steps that 3 Blue 1 Brown laid out, or that Ben Page just laid out, you'll be able to solve probabilistic problems a lot easier, and you'll also start to refine and hone your intuitions to be in line with proper probabilistic reasoning. But onwards we march to perhaps the most important section in the whole video. We'll basically be taking what we've learned so far and seeing why certain kinds of thinking are fallacious or mistaken. So one common mistake is one we've already seen, or at least one we've already hinted at, and it's the base rate fallacy. This basically amounts to ignoring prior probabilities when trying to assess how probable a hypothesis becomes in light of certain evidence. So recall the odds form of Bayes' theorem. The posterior ratio is equal to the likelihood ratio times the prior ratio. Notice that the ratio of the posteriors is a function not just of the likelihood ratio, but also of the ratio of the priors. Oftentimes, without recognizing it, we'll ignore the ratio of the priors when trying to determine the ratio of the posteriors, and will instead only focus on the likelihood ratio. That's disastrous, since even if the likelihood ratio is very top-heavy, the prior ratio may be very bottom-heavy. And so if we ignored the prior ratio, we'd mistakenly conclude that the posterior ratio was significantly top-heavy, and hence that the posterior probability of the hypothesis is very high after conditioning on the evidence in question. This is a mistake. You need to take into account the priors. This sort of reasoning is also known as the base rate fallacy, or base rate neglect when thinking about statistical problems. The base rate of a feature is basically just the prevalence of that feature within the population at large. Oftentimes we neglect this prevalence in assessing the probability that some hypothesis is true. For instance, in assessing whether or not someone has cancer. We often neglect that base rate and instead focus on the likelihood of the evidence on the hypothesis. This may have been what happened to you in the opening problem of this video. You may have failed to take into account the 1% prevalence of cancer in the population and focused instead on the probative or evidential value of the positive test result. This may then have skewed your assessment of the probability that the woman had cancer towards it being much more likely that she had cancer. But as we've seen, that's mistaken. Yes, while the test is 90% accurate, and so counts as reasonably good evidence that the woman has cancer, the prevalence of this cancer in the population is still very low. And when you plug in all the numbers, the overall probability that she has cancer is only 8%. And the reason is that among the people who test positive, most of them, in fact 92% of them, are false positives. This shows the importance of taking into account both the evidence and the base rates, or priors. But also, of course, don't be too focused on the prior. There is a kind of dogmatism where someone thinks that a hypothesis is so implausible that they either don't consider evidence against it, or they ignore evidence against it, or they downplay evidence against it, or they think no amount of evidence could overcome their prior. Those are also all mistakes. So anyway, that is the first mistake that we're going to cover. The cancer example also illustrates another common mistake in reasoning, namely inferring from the fact that there's a strong piece of evidence for a hypothesis that the hypothesis must probably be true. No, that's incorrect, right? Just because E is evidence for H, indeed just because E is very strong evidence for H, it doesn't follow that E makes H probable. H could still be very improbable overall. Remember, to say that E is evidence for hypothesis H is just to say that E raises H's probability. That doesn't mean that E makes the hypothesis probable. Before taking the evidence into account, the hypothesis might be only 1% probable, and afterwards it might be 5% probable. Notice that the evidence here has raised the probability of the hypothesis, but it clearly doesn't make the hypothesis probable. In other words, it didn't render the hypothesis probably true, or more probable than not, or anything like that. So never infer from the claim that, say, fine-tuning is evidence for theism, that theism is therefore probably true, and never infer from the claim that, say, evil is evidence for atheism, that atheism is therefore probably true. Those don't follow. To determine whether theism or atheism is probably true, you need to take into account their prior probabilities. And not only that, but you also have to take into account our total range of data, our total range of evidence that bears on these hypotheses. And this too bridges into another common mistake in reasoning, which is ignoring the total evidence requirement. According to the total evidence requirement, also called the requirement of total evidence, when assessing the overall probabilities of hypotheses, we should take into account all of the relevant evidence at our disposal, instead of just some proper part of that evidence. You may determine that, after conditioning on some evidence E, a hypothesis is more probable than its negation. But if that's the only evidence you're taking into account, and there are other pieces of data that bear on the probability of this hypothesis, then you're not licensed to conclude, after only examining E, that the hypothesis on the whole, all things considered, is more probable than its negation. To infer that, you need to take into account the total range of data or evidence that we have. So, for instance, even if you have a Bayesian argument from evil against the existence of God, and even if you take into account both the likelihood ratio and the prior ratio, and even if you conclude from this that the ratio of the posteriors heavily favors atheism, you can't then conclude that atheism is probably true, all things considered. You need to take into account other relevant evidence, like fine-tuning, divine hiddenness, consciousness, religious disagreement, religious experience, and so on. The same is true for Bayesian arguments for theism, of course. And closely related to the total evidence requirement is the fallacy of understated evidence, which is the next mistake in Bayesian reasoning on our list. And we're going to hand it over here to Relay Theology to explain what the fallacy of understated evidence is, and to offer a concrete, tangible application thereof.
Let's say a couple with two small children moves in across the street from you. They also drive a brand new car. Now, you just happened to be reading earlier that day that this particular model and year scored the highest in its class in every single safety measure across the board. You also learned that this car costs significantly more than other cars in its class, specifically because of this high safety rating. Given the total evidence available to you at this time, you reasonably infer that your new neighbors probably care a great deal for safety for their family. You wait a few days, allowing them to settle in before crossing the street to introduce yourself. However, as you walk up their driveway, you notice that the airbags have been tampered with and disabled, and that the child safety seats are both attached improperly with duct tape. Naturally, you're a bit puzzled. Observing the general fact that your neighbors purchased a car specifically pricey for its safety features clearly seems to be more likely on the hypothesis that the family cares about safety than on the hypothesis that the family does not care about safety. And yet, given the general fact, the additional observations, the specific facts of the duct-taped child safety seats and disabled airbags, are more likely on the hypothesis that the family doesn't care about safety than on the hypothesis that they do. Now, if, say, somebody was in a position to know all of these facts, the general and specific facts, but yet they presented an evidential argument for the hypothesis that the family cares a great deal for safety, but appealing only to the general fact about the car's high safety rating and related high cost, they would be guilty of understating the evidence. Philosopher Paul Draper argues that many evidential arguments for theism are similarly guilty of appearing convincing only because they understate the evidence, as they, quote, successfully identify some general fact about some topic that is more surprising on naturalism than on theism, but all too conveniently ignore more specific facts about the topic, facts that, given the general fact, are significantly more surprising on theism than on naturalism. There are many examples of arguments for theism which fit this pattern. One such argument sets its sights on religious experience. If we agree that the general fact of religious experience had apparently of God, is more likely on theism than on naturalism, we can say it counts as some evidence for theism over naturalism. But Paul Draper reminds us that the general fact of the existence of religious experience is not the only relevant fact we know about that topic. Draper reminds us of three specific facts which, given the general fact of religious experience, are much more likely on naturalism than on theism. First, quote, not everyone has theistic experiences, and those who do typically have a prior belief in God or extensive exposure to a theistic religion. Secondly, the subjects of theistic experience pursue a variety of radically different religious paths, none of which bears abundantly more moral fruit than all the others. And third, victims of tragedy are rarely comforted by religious experience. Again, given the general fact of the existence of theistic religious experience, each one of these facts are more likely on naturalism than on theism. And so after considering all the relevant facts about religious experience, it's not at all obvious that relevant observations regarding the topic of religious experience actually favor theism over naturalism. Just as when considering all the facts about your neighbor's car, it's far from obvious that they give a damn about their children. According to Draper, many evidential arguments for theism suffer similarly.
And what matters more here is more the fallacy of understated evidence and at least understanding the content of that than whether or not you agree with Draper's assessment there. Another pretty important mistake that you should be aware of and avoid is ignoring the comparative nature of Bayesian confirmation. We already covered this, but this is worth keeping in mind as a separate mistake that you need to avoid. Right, recall that E is evidence for H if and only if the ratio between the likelihoods of H and not H is greater than 1. E is more expected or more probable or more likely on H than it is under the negation of H. Notice that this is essentially comparative. We're comparing how likely E is under H to how likely E is under not H. And again, even if E is very improbable under H, E can still be very powerful evidence for H. What matters is that E is still more probable under H than it is under the negation of H. Another mistake, which is kind of related, is demanding strict, precise numerical likelihoods of the data conditional on the hypotheses in question. The thing is, when you have the comparative nature of Bayesian confirmation firmly in mind, you can see that that isn't strictly necessary, at least for many purposes. We saw this actually when we watched Ben Page's video on the Bayesian bar, right? He still showed the utility of the Bayesian bar and Bayesian reasoning even if you don't assign precise numerical credences. And Richard Swinburne also writes that to accept that Bayes' theorem governs all claims about the support given by evidence to hypotheses does not involve holding that the various probabilities can be given exact numerical values, and as he noted earlier, inductive probabilities do not normally have exact numerical values. One can think of them as having rough values, values within certain limits, and one can think of the theorem as putting limits on the values of some probabilities, given the limits on others. Another mistake you might see in reasoning is that you might hear someone say that some data E obtaining would be evidence for hypothesis H, but E not obtaining wouldn't be evidence against H. But that is mistaken. If E is evidence for H, then not E is evidence against H. You could also say if E would be evidence for H, then not E would be evidence against H. Importantly, this just follows from Bayes' theorem. So for instance, if seeing a limb grow back after prayer would be evidence for the efficacy of prayer, then not seeing a limb grow back after prayer would be evidence against the efficacy of prayer. So let's see why this is the case, what I'm going to be calling the evidential symmetry thesis. If E is evidence for H, then not E is evidence against H. So that's our goal. Our goal is to establish this thesis. So suppose that E is evidence for H. Then it follows that the likelihood ratio, the ratio of the likelihoods of H to not H, is greater than 1. E is more expected on H than it is under not H. So this ratio here is top-heavy, and hence when you divide the numerator by the denominator, it's greater than 1. Let's just say the probability of E given H is x, and then the probability of E given not H is x minus n. So n is just going to be some positive, non-zero real number, of course less than 1. This is just a way to mathematically represent how this is greater than 1, right? Because x is going to be greater than x minus n, given that n is a positive real number greater than 0 and less than 1. So we got the probability of E given H being x, and we've got the probability of E given not H being x minus n. But notice that the probability of E given H plus the probability of not E given H is equal to 1. I actually proved this mathematically for patrons in the script, but I hope you can see that it's just like intuitively obvious. So for instance, if it's 40% likely that it rains given that it's cloudy, then clearly it's going to be 60% likely that it doesn't rain given that it's cloudy. Or if it's 1/6 likely that the die rolls a 1 given that the die is fair, then clearly it's going to be 5/6 likely that the die rolls something other than 1 given that the die is fair. These things have to add up to 1. If a hypothesis predicts the truth of some data with 20% probability, then clearly the hypothesis will then predict the falsity of that data with 80% probability. So it makes sense if you think about it. It's self-evident, you might say. Rearranging this, so we're just subtracting probability of E given H from both sides, we get that the probability of not E given H is equal to 1 minus the probability of E given H. And notice that the exact same sort of reasoning here can be applied when the hypothesis is not H instead of H. Right? It's the same idea. If the hypothesis not H predicts the truth of some data with 30% probability, then that hypothesis not H will also predict the falsity of that data with 70% probability. So this will equally be true if we plug in not H for H, and hence we can plug in not H for here and here, because this just followed from the preceding step. And that, of course, just gives us this. But recall that the probability of E given H, we let that equal X, and the probability of E given not H, we let equal X minus N. So we have the probability of E given H here and here, we have the probability of E given H here and here, and so from all the preceding we get this. Notice here that probability of not E given H shows up right here. The probability of not E given not H shows up here. Remember that the probability of not E given H is equal to 1 minus the probability of E given H, which just equals X. So we do 1 minus X up here. And then the probability of not E given not H is equal to 1 minus the probability of E given not H. And remember, the probability of E given not H is just X minus N. So we have down here 1 minus X minus N. And of course, this here equals 1 minus X over 1 minus X plus N. And that, of course, equals 1 minus X over 1 minus X in parentheses plus N. And notice that that has to be less than 1, right? You have a number here, and that number in the parentheses is the same number as this, and then you add a non-zero positive real number to that. And so the numerator has to be less than the denominator, in which case this fraction as a whole is less than 1. And so look what we've just concluded. This is the likelihood ratio for the hypotheses H and not H with respect to the negation of E. This is that likelihood ratio here and here. So this has to be less than 1. That is what we just concluded. And so look what we just proved. We just proved that if the ratio between the likelihoods of H and not H with respect to the evidence E is greater than 1, then the ratio between the likelihoods of H and not H with respect to the negation of E is less than 1. In other words, we just proved that if E is evidence for H, then the negation of E is evidence against H, right? Because here E is more expected under H than it is under not H, because this fraction is top-heavy, and so E is evidence for H. But in this case, because this fraction is less than 1, it's bottom-heavy. So that means the negation of E is more expected under the negation of the hypothesis than it is under the hypothesis. And so the negation of E counts as evidence against the hypothesis and for the negation of that hypothesis. So anyway, that vindicates our goal. Our goal was to show that if E is evidence for H, then not E is evidence against H, and we just showed that. Also, again, the patrons have access to the script, which actually, because I just recently added this additional proof, the script went up to 40 pages, I kid you not. But there's an additional proof for patrons, which goes through a different route. So again, that is what I call evidential symmetry. And it's pretty significant. Consider the meager moral fruits argument or whatever against Christianity. One very simple way that you could put that argument is imagine if all and only professing Christians were like noticeably morally superior to literally everyone else. Like, despite the fact that, they have very similar social structures to other churches, they have similar support groups to other churches, they eat roughly the same things, etc. Suppose that really the only thing that differentiates them from other groups is that they are professing Christians. And of course, that also they are noticeably morally superior to everyone else. I think it's obvious that if we were to see that, that would be significant evidence for Christianity. This is the fruit of the Spirit. It's God's grace working through people. It's the transformative power of Christ or the Holy Spirit or something. I don't know. The point is just that I think it's obvious that this would be some evidence for Christianity. But then it just deductively, strictly, logically follows from that if we don't observe that, and of course we don't, then that is at least some evidence against Christianity. So it's relevant, for instance, to the meager moral fruits argument. It's also relevant to lots of other arguments and just to reasoning more generally, so that's why it's important to keep in mind. So anyway, that's evidential symmetry. Importantly, though, something that isn't necessarily symmetric is how strong the evidential confirmation or disconfirmation is. So even if, in my imagined scenario, we had super strong evidence for Christianity, it doesn't necessarily follow that we thereby have super strong evidence against Christianity in the fact that we don't witness that. It does follow that we have evidence against Christianity, but it doesn't necessarily follow that we thereby have super strong evidence against Christianity, despite the fact that observing the data would be super strong evidence for Christianity. So this is an asymmetry in the strength of evidence. Just because evidence or data E would be very strong evidence for H, it doesn't thereby follow that the negation of E would be very strong evidence against H. Again, it would be evidence against H. Don't get me wrong. We just proved that earlier. But it doesn't necessarily follow that it would be very strong evidence. So to illustrate this, imagine that our data is that the stars in the night sky spell out the first 14 verses of the Book of John in perfect Koine Greek. And let T be theism and not T be atheism. Now, this data would be astronomically improbable under atheism, but it's also very improbable under theism, right? Like, out of all of the ways that God could have designed the universe to be like, only a very tiny fraction of those have this precise manifestation of divine power. So let's just get some toy numbers on the table to illustrate the asymmetry of the strength of evidential support. Again, this is just an illustration. Don't split hairs over the numbers. I don't care if they're realistic. This is just an illustration. So again, we've got E, T, and not T. Let's say that the probability of the evidence given atheism is 1 in a billion. So that's that really tiny number here. And what follows from that, of course, is that the probability that we wouldn't see the evidence given atheism is 99.99999, etc. percent. By contrast, the probability of the evidence given theism is still pretty small, right? It's 1 in a million, and so the probability is 0.000001. And what that means, of course, is then that the probability that we wouldn't see the evidence given theism is 99.9999% likely. So if we observe E, if we observe that evidence, here's the likelihood ratio, or Bayes factor, indicating the strength of evidential confirmation of theism. Right, it's going to be the probability of the evidence given theism divided by the probability of the evidence, and that is, of course, 1 in a million divided by 1 in a billion, which amounts to 1,000 to 1, or 1,000. That's the Bayes factor, that's the likelihood ratio. Now that is very powerful evidence. By contrast, if we observe not E, that is, if we observe that it is not the case that the stars spell out the first 14 verses of John, the likelihood ratio, or Bayes factor, indicating the strength of the evidential confirmation of the negation of T, right? So here we're putting the negation of T on top because we're looking at the strength of the evidential confirmation of not E for that, so I'd like to put it on the top. I think it's just easier. The likelihood ratio, or the Bayes factor in that case, is 1 minus 1 in a billion divided by 1 minus 1 in a million. And that gives us 1.000000999. So it's greater than 1. This is evidence for atheism, the fact that we don't observe the stars spelling out the first 14 verses of John, given these probability assignments. It does count as evidence for atheism, but obviously it's nowhere near as strong evidence for atheism as observing that data would be for theism, right? So E is very powerful evidence for theism, but the negation of E is only very, very weak evidence for atheism. What this tells us is that even though E would be evidence for T, while the negation of E would be evidence against T, the strengths of these evidential confirmations are not guaranteed to be the same. The reasoning that we just went through also indicates the importance of falsifiability, or better, disconfirmability, as a theoretical virtue. If there's nothing in principle that could disconfirm or count as evidence against a hypothesis, then there's also nothing in principle that could confirm or count as evidence for that hypothesis, right? This just follows from the previous section that we went through. Right, remember, we just saw that if E is evidence for H, then not E is evidence against H. And so if there's nothing that could count as evidence against a hypothesis, then nothing could count as evidence for that hypothesis either. And this is why, in general, unfalsifiable, or better, non-disconfirmable theories are quite bad. There can't be any evidence for them, at least assuming the positive relevance account of evidence, that is, construing evidence as probability raising. The final mistake I'll cover here, and believe me, there are more mistakes besides, is a mistake I call likelihood ratio rigging. And I'm going to give an example of this from one of my earlier videos. It's the most popular video on my channel. It is 12 hours long, and it is called Over 100 Arguments for God Answered. This is a purported argument for God's existence. Premise 1 says, given that God intervenes to produce life on Earth, there is no chance at all that there will be no life on Earth. Premise 2 says, if God does not intervene to produce life on Earth, the probability that life will occur here is very low. Right, so look, these are conditional probabilities. We're establishing a likelihood ratio. This is saying, given the hypothesis that God intervenes to produce life on Earth, it is guaranteed that there will be life on Earth. So the probability of life on Earth, given that God intervenes to produce life on Earth, is 1. But by contrast, the probability that there's life on Earth, given that God does not intervene to produce life on Earth, is very low. So look, we have a likelihood ratio that very strongly favors the hypothesis that God intervenes to produce life on Earth. You could find the same likelihood ratio given that Zeus intervenes to produce life on Earth. And then the next premise, it is just as reasonable to bet that God will intervene to produce life on Earth as that he won't. So there's a 50% chance of that. And so that's talking about the ratio of the priors. That premise is certainly false. So yeah, the basic idea behind likelihood ratio rigging is that you can always artificially bake something into your hypothesis that entails or strongly probabilifies the data. But when you do this, you're very often purchasing predictive power at the cost of correspondingly lowering the prior probability of your hypothesis. You're decreasing the ratio of the priors by the same proportion in which you increase the likelihood ratio, and so there's no overall effect on the posterior ratio, and hence no overall effect on the posterior probability of your hypothesis. So yes, I forgot to show this slide when I was saying that. Take the example of playing poker. I'm the dealer, and of course I give myself 5 royal flushes in the row. Here is me scheming my plan. You accuse me of cheating. I say the shuffling is fair. You go on to explain how the probability of 5 royal flushes, given the cheating hypothesis, is much, much, much greater than the probability of 5 royal flushes, given fair shuffling, and that the probability of me cheating is only mildly more improbable than the probability of fair shuffling. And hence we should conclude, assuming the only relevant evidence here is the 5 flushes, that I probably cheated. And the reason why you think, probability of cheating is only mildly more improbable than the probability of fair shuffling, maybe you've been with me in the past, you know that on occasion I cheat on card games. This is not actually true. Again, this is just part of the imaginative situation. I don't cheat in card games. I'm fun, I swear. But part of the imaginative situation, you've been with me for a few years. Occasionally I cheat. You know that generally I don't. Generally I'm a person of integrity. But it's certainly not totally out of character for me to do it. So although it's improbable, it's not like vastly, vastly improbable. At the very least, the contrast between these two probabilities is nowhere near as large as the contrast between these two. So you got a fairly convincing argument here for the fact that I cheated in light of this evidence. But alas, I'm not convinced. Here's what I'm going to say. Let's make my hypothesis that the shuffling was fair and that this fair shuffling gave me 5 royal flushes. Now I predict the data just as well, indeed better than the cheating hypothesis. Right? My hypothesis just entails the data. By contrast, under the cheating hypothesis, okay, one way I might have cheated is giving myself 5 royal flushes, and that's not super duper improbable under that hypothesis, but also I might have cheated in other ways. I could have given myself only like 4 royal flushes, or maybe 3 or something like that, or maybe hands that were slightly worse than royal flushes. So actually, my new hypothesis that the shuffling was fair and that this fair shuffling gave me 5 royal flushes, I actually predict the data better than the cheating hypothesis. So you don't actually have evidence for the cheating hypothesis and against my newly modified fair shuffling hypothesis. So take that. Now, I hope at least intuitively you see that my reasoning here is just absurd. Yes, it's true that you no longer have evidence here. This is true, right? Keep this firmly in mind. It is true here that you no longer have evidence against my newly modified shuffling hypothesis, since the data is actually more expected on my newly modified fair shuffling hypothesis as it is on the cheating hypothesis. But the problem is that I've only purchased this increase in predictive power at the price of drastically decreasing the prior probability of my hypothesis. In fact, the factor by which my prior probability decreased is the same as the factor by which the original fairness hypothesis was disconfirmed by the evidence. Since the probability that the shuffling was fair and that this fair shuffling gave me 5 royal flushes is just equal to the probability that the shuffling gave me 5 royal flushes, conditional on the claim that the shuffling was fair, multiplied by the probability that the shuffling was fair, right? This is an instance of the ratio formula that we covered earlier on in the video. So when we look at the posterior ratio equals the likelihood ratio times the priors, what I've done in modifying the hypothesis from the fair shuffling to the hypothesis that the shuffling was fair and that shuffling gave me 5 royal flushes, what I've done is I've merely shifted the improbability from the numerator of the second term here, right? The improbability that I'd get 5 royal flushes given that the shuffling was fair. I've shifted the improbability from this term here, right? The likelihood of the fair shuffling hypothesis. I've shifted the improbability from there to the prior, right? Now my prior that fair shuffling gave me 5 royal flushes is just correspondingly lowered improbability. You can actually mathematically show in the example that I gave that the ratio of the posteriors when the hypotheses in question were fair shuffling and cheating, that's exactly the same as the ratio of the posteriors when the hypotheses are my newly modified hypothesis that fair shuffling gives me 5 royal flushes and the cheating hypothesis. And so by modifying my hypothesis to purchase that predictive power and by correspondingly diminishing my prior probability, I actually didn't do anything to boost the epistemic credentials of my hypothesis. It's in the same sucky situation as before. The posterior probability is going to be exactly the same. And this point quite easily generalizes. Again, you can always bake into your hypothesis something which renders the data very probable, or even entails the data. But be careful when you do that, since that may very well just correspondingly lower the prior probability of your hypothesis. If so, then you haven't actually made any probabilistic headway. The posterior probability of H, that is, the probability of H given E, is going to be the same before and after modifying your hypothesis in this way. Again, this isn't always the case when someone's hypothesis entails some data. I mean, sometimes it's a very natural consequence of a view, and, someone just isn't like artificially baking into some core hypothesis an auxiliary which entails the data. So this mistake isn't always present whenever someone's hypothesis entails the data, okay? Just keep that in mind. This is, again, just something that you need to be very wary of. So, at last, we've finally reached the end of the video. It's time for me to break down in tears and give an inspirational speech. No, Bayes' theorem is really important. It offers us a precise, mathematical way to rationally update our credences and beliefs in light of new evidence. My goal in this video has been to give you a solid foundation, not only for understanding Bayes' theorem, but also for applying it and seeing its profound significance. Before leaving, though, I want to put some resources on your radar. 2 very important books in this area that you should definitely check out if you're interested are by Michael Teitelbaum. It's called The Fundamentals of Bayesian Epistemology. It's like a 2-volume series or whatever. The first one is Introducing Credences. The second one is Arguments, Challenges, and Alternatives. I've drawn heavily on these in making this video. 2 more books that I've drawn on in making this video are David Papanow's Philosophical Devices, Proofs, Probabilities, Possibilities, and Sets, as well as Eric Steinhardt's, more precisely, The Math You Need to Do Philosophy. And 2 other relevant books are Ian Hacking's Introduction to Probability and Inductive Logic, as well as D.H. Mellor's Probability, A Philosophical Introduction with Routledge. As for websites that you can go to learn about these things more, you can check out various SEP entries, the Stanford Encyclopedia of Philosophy. Alan Hayek has one on interpretations of probability. There's an SEP entry on Bayes' theorem itself, although that one's going to be far more technical than my video here, so beware. Anyway, I always recommend the Stanford Encyclopedia of Philosophy. And you can look at the references therein as well to follow things and pursue things in more detail. As for videos, you can check out my newly created Bayesianism and Probability playlist. It only has 1 video of mine, but lots of other videos that will help you through these topics. And if I make videos in the future on probability or Bayesianism or things like that, they will go in that playlist. And of course, more generally, right, check out my playlists. I've got playlists on the Kalam cosmological argument, teleological arguments, ontological arguments, contingency arguments, discussions with philosophers, and everything in between. So definitely check out my playlists. Oh, I even put a slide for them, so yeah, that's how much I cared about this. Now, if you've made it this far in the video, I extend my sincere congratulations. This video was not easy to get through, and you showed commitment, intellectual curiosity, and intellectual perseverance, so I heartily praise you for that. And I hope my literal dozens of hours of working on this have helped you gain a greater understanding of reality. If you enjoyed it, please hit that like button, subscribe, turn on that little bell for notifications, consider supporting me on Patreon or tipping me through a one-time donation, right? If you tip waiters who get paid for what they do, consider tipping me who made this video for free, who spent way longer than waiters do in helping you, and who's helping you try to get to the fundamental nature of reality and not just helping you get some more breadsticks. So you can do that one-time donation via PayPal, link is in the description. Any amount helps, truly any amount. And as always, what better way to end is there than I'm Joe Schmid, this is The Majesty of Reason, and peace out.